we could kind of get the main graphics API in like 100 lines or something, like not like 20,000 lines like Vulkan is. The drivers are complex, but also it's so complex to use the APIs, and modern hardware doesn't need that kind of like abstraction anymore. Rage had virtual texturing like 3 DVDs, and DVDs have massively slow seek times because virtual texturing is super fine-grained, so it can seek a lot. But we were only running on the hard drive, so it was completely fine. We had much less texture popping than anything else.
I would be super interested to understand how did you start with rendering, because like that's like kind of dark arts of programming, like graphics programming, and it's, at least as far as I see it, it's quite difficult to get into. And you seem to start this very early in your career. So can you tell me like how did it happen?
I have been doing games like for really long time. Maybe I was like 12 or something. Like when I started, like my friends had like, yeah, they had like game consoles, and one of them have C64, and we were doing some kind of games on that. Like it's basically like back in the day, like there was some like basically like how would I say it? Like it's a Finnish magazine called Microbitti back then, and they were listing these programming lines for that you could copy on your computer, because there was not that many games, and people were kind of kind of trying to find the games and copying, of course, from friends. And there was even some kind of radio channels that were kind of broadcasting at that you could record and kind of pirate games that way. But yeah, it was a really long time ago, and we were just copying those things. We didn't really know like how they worked and so on. But then once you do that and kind of you try to fiddle around, and then you notice that okay, it something works and you can change it somehow. And my father got an X86, like just a normal computer. Like there was no games or nothing, monochrome display and anything. So we were making some kind of games with text mode because it didn't really have proper graphics with only 2 colors and everything. But that's pretty much where I started, like just making text mode games on that computer. And it was of course really slow and only floppy disk and everything. But then of course father got a new computer and it was running 3D Studio Max, and yeah, that's kind of like how we started making 3D models, like just experimenting with that. And yeah, and of course, like yeah, all that basic tools at that time, like Deluxe Paint and so on. Like Deluxe Paint had really nice functionalities, like you could do one sprite and then it could kind of run this kind of small script that you could kind of rotate the image and so on. So you could basically create the whole sprite sheet in the program. It was really nice for that kind of, and it could, like inside the program, you could also do palette animation and everything. So many game developers back then were using Deluxe Paint, and I was also using that and kind of exporting the assets and sprite sheets from that to my own like 2D renderer back then. And it was actually the first time I was writing assembly language, and because like I was writing Turbo Pascal back then, so not before I started writing C and C++, and of course the language was pretty fast. It's almost as fast as C, but back then compilers were really bad. So if you write your own assembly blitters, like for the sprite blitters and blending and so on, then it was much faster. So it allowed us to do like games that actually had pretty nice looking graphics and alpha blending and everything on CPU. So that's pretty much where it started. And for that kind of simple 2D renderer, like I made a lot of games. And in the Finland there was this kind of Finnish game scene back then, like a lot of indie games. People were pushing them to BBS systems because of course internet was not really widely available, but there was, you could call with your modem to a BBS system and download games from there, and we were sharing games, and the same magazine, the Microbitti magazines, they didn't publish like code listings anymore, but they published like this kind of, there was a couple of pages for this kind of Finnish game scene, like this indie scenes, and they were every month selecting the best game, like the best kind of Finnish indie game, and I was also nominated a couple of times there, so we were kind of
Nice.
competing with the guys guys in the Finland to kind of see like who was going to make the next monthly best game, and they were always selecting. The magazine was selecting that. So yeah, there was a pretty nice scene of like indie game developers running in Finland in the 90s.
How do you fit in then in this picture? What do you do? Because have you attended university or?
Yeah, I was university. I actually dropped out of the university for a short time, but then I joined
Came
back
back?
and made my got to graduate later. But it was kind of interesting story. When I was like 23 years old, I was called by the Redling studio. Like that was one of the oldest Finnish studios. They were making the Trials game series. Like not at that time. They got a big contract from Nokia. They were making the N-Gage game console, like the handheld console. Everybody was laughing because it was side talking and everything. Like I don't know if you remember that, but it was Nokia was the biggest mobile phone vendor at that time. It was the biggest company in the whole Europe, like the most valued company. It was selling more phones than Apple and Samsung are selling together right now. So it was a really big company, and they were doing this kind of game console because there was Nintendo DS and Sony PSP, and they wanted to compete on the handheld game consoles. But like, how would I say, like they gave a lot of money to the company, a big project. So I was hired as a lead programmer because I had like experience doing like my own game engine projects and so on, and then we kind of had a team there to build a game. We were building the flagship game for the Nokia N-Gage launch. At that point, it was really secretive at the beginning. Like Nokia was like back then, like these kind of business companies were really secretive. We needed to have like two separate, like we couldn't connect our development computers to internet at all. Like we had separate laptops for internet and then dev computers separately on a separate internet because they were
Wow.
worried that something will be stolen or something like that. Yes.
Can you explain the virtual texturing? Like, what would be the trick behind it?
Yeah, the virtual texturing is kind of a texture streaming system, but it's really fine-grained. You are splitting the texture to really small tiles, like 64 pixels or 128 times 128 pixels. And when you are rendering, you are first rendering this kind of UV pass, like which UVs you need from which texture. So you are rendering a kind of full screen pass of like what texture data you would need to render this scene. And then of course, you cannot read it back to CPU immediately. You are rendering with that, but there is some kind of feedback like coming from the GPU to CPU, and you are analyzing every frame, like what data you are missing, and because all the textures have MIP maps, you are kind of like loading coarse MIP maps first, and then when you notice on the screen that you need some more detailed data of something, like you need that, you know that okay, this UV needs to be on this location, you need more fine-grained MIP level, then the streaming system will provide it you eventually. It will queue up those and prioritize and everything and just stream from the hard drive all the time. Like we couldn't, like it was nice on Xbox Live Arcade because all of those games were installed to the hard drive. Virtual texturing is really, really bad on discs. Rage had virtual texturing like 3 DVDs, and 3 DVDs have massively slow seek times because virtual texturing is super fine-grained, so it can seek a lot. But we were only running on the hard drive, so it was completely fine. We had much less texture popping than anything else because the big AAA games could not really use that really well because back then you had to ship them on disk and you could not install to the hard drive because the hard drive was so small. It was only designed for save games and such. So games were not installed to the hard drive. But of course on Xbox One and PlayStation 4 you would install the games on the hard drive as well. So then at that point like AA games could start using these kind of technologies better. But Rage was the first one and Carmack was optimizing it like crazy. So they managed to ship it. Of course it had a lot of texture popping, but we had much less. And one thing also that we shipped, that we had this fully virtual texture terrain system, which was like fully dynamic virtual texture system. The interesting thing about that is that like a lot of games afterwards started using that tech, like Battlefields, or like everybody basically, all the Ubisoft games like Far Cry and so on, they were using that kind of technologies for the terrain rendering. The dynamic virtual texturing is basically like you have massive virtual texture, like let's say like 4 million times 4 million pixels, and of course like you know that there is no way you can store it anywhere. So it's a kind of just virtual address space, and when the virtual texturing system says that I need this kind of style of the texture for the terrain rendering, then you will generate it. And the generation is like you are blending texture, there are blending masks and so on, and then there's a lot of decals, like all the road decals. Like you had like we had massive amount of decals. There could be like 10 times or 20 times decal overdraw on some places on the terrain, but it was still running perfectly because you are not blending the decals every frame. You are only blending them together when the virtual texturing system says that there is a page miss. I need to have you to generate me this page, and then you generate the page, and you will use it for like hundreds of frames. So you kind of amortize the whole cost of decaling. And this was super nice because the terrain looked nice and you could alter it. You could make the whole terrain really small because it was an Xbox Live Arcade game. You had to download the game. And back then, of course, people didn't have fast internet access. So it was like 350 megabytes or something for the whole download. So the terrain had to be small. So we used this kind of technology. And the interesting thing about this tech is that it's really similar to what we used on the Warhammer game, like on the Sony PlayStation. But the PlayStation game had this kind of fixed camera angle. It was kind of strategy game. So we were creating this kind of rectangular area of kind of scrolling virtual texture on that area instead of these small tiles. So it was kind of one area we were just rendering on the edges when you were scrolling the camera, like blending the terrain, decals and everything. So we're kind of blending the decals on this kind of scrolling map. But now with the virtual texturing, if you have 3D scene, you have like lot of view range. Like we had like I think 2 kilometer view range on those trials games, like a 16 square kilometer like terrain, so that you can build your tracks on there. There was one track that was going through the whole like 16 square kilometer area called Giga Track. It was like hilariously long, and you could just play it for ages. And the streaming tech was just handling it. It was really nice, and but it was kind of interesting that we were using kind of old technology but combining it to this kind of page creation. The virtual texturing allowed us to create the old like dynamic terrain texturing tech to bring it to 3D worlds instead of like this isometric 2D worlds. So, but the idea was old. So that like how do you create terrain texture by blending a lot of decals together? So, and basically everybody started using that. It wasn't like that we started the craze, like everybody else came to the same conclusion that you cannot store this kind of massive terrain texture. You need to blend it, and you don't want to blend it like just at kind of triangle granularity or like vertex granularity. That looks really bad. So people wanted decals, they wanted roads, they wanted like all of these things that are not kind of on a grid. So, but of course, back in the day, and still there are a lot of games that are like the terrain texturing looks like shit because they are just blending like on a grid, which doesn't look good. So definitely, like if you want terrain rendering tech, like you still want to use this kind of decal-based virtual texturing system for your terrain, and that's what Ubisoft has been using for a long time, and they also. I think on Far Cry 4 they had a presentation about like even more advanced version of this technology.
I know that the next chapter is Claybook, right?
Yes.
And the second order. So you mentioned that you left with the art director,
Yes.
the technical art director. Is this like
Yes.
the person with whom you got to work on the second order?
Yes.
Okay.
Yeah, Sami Saaren, he was the technical art director of the Red Link studio back then, and he was really like not like a director in a way. He was really hands-on, like doing stuff. Like he was managing outsourcing as well, but he was really like good at doing art and really good at doing like technical art and shaders and everything. And he was writing program code as well if needed. So it was really nice to go with him because he could have made the game on his self basically because we took like we started using Unreal Engine, so yeah, he could have made a game with Unreal Engine himself, but the Claybook was actually a technically really demanding game because it was a clay simulation game. We wrote a whole new like, or I wrote like it was just me, like not we at that point, but basically it ended up being in a way that I was writing tech code and he was doing everything else. so, so as a hindsight, we should have had a designer in the project and maybe some gameplay program as well, because it wasn't really optimal setup. But for me, it allowed me to really focus on computer ray tracing, like distance field ray tracing, like this kind of sparse data structures on GPU. I wrote my own GPU physics engine as well, which was running on the GPU as well. And
physics on GPU?
because it GPU based physics engine, yes. Like there was a clay simulation engine and then like fluid simulation as well. Like the clay and fluid, everything was running on the GPU. And the game world data structure was also on the GPU. It was like 1 gigabyte of like volumetric data on the GPU. And yeah, there was some readbacks to CPU, and CPU was doing some lightweight like bookkeeping, but most of the game logic was actually running on the GPU, on the Claybook. So it was kind of an interesting game in a way. In a hindsight, don't do that. It's really painful because GPUs are not really good at running this kind of branchy gameplay code. They are really good at running this kind of really data optimized, cache optimized small code. And GPUs don't have good debuggers, or they do have debuggers, but they are not like that you iterate through the code like one line at a time. You can read results between row calls and so on, but you cannot like. There are tools that allow you to kind of step through shaders as well nowadays, but back then there was none of those things. So it's really hard to write this kind of fine-grained like gameplay code on GPU. It takes a lot of time, and you have to optimize everything ahead of time to be runnable on that architecture. Everything needs to be parallelizable and so on. So writing gameplay code for that kind of architecture is really slow. So I wasted massive amount of time of that. And if we would have had like more traditional game, we could have had iterated much more on kind of like what the game is and so on. So we didn't have much time, and then of course our money was running out eventually. So it was like a 3-year project. We got some one angel investor on it, and then there was a Finnish technology fund called Tekes. They were funding like they are kind of taking these small startups, and they are paying like half of the first year salaries. So if you get their grant, you of course have to do a lot of paperwork, which took like 2 weeks to do, like massive amount of like planning and design documents and so on. But we had to kind of think about what the company was all about and do all the company stuff, like all the LLC stuff. Like we had to do them to get the Tekes grant, and then they paid half of our salary for the first year. And it was important, of course, for our because the investment was so small. So originally, like we had kind of money for 2 years, but then we got one extra loan for the Tekes as well. Like they are loaning for these startups. If they have been giving them funding, you can get a loan with really good terms, and you only need to pay like half of that back, or like 70%, or I don't remember exact numbers anymore, but they are kind of supporting Finnish technology startups, and we were doing our own physics simulation tech and our own like ray tracing tech and so on. So we kind of said to them that it's a tech project, and it was a tech project. Like it was really a tech project.
You didn't lie. You didn't lie.
Yeah, I didn't lie. It was heavy tech project. It was also a game project. They don't support direct, like if you are bringing them just a game project, like normal Unreal Engine game project, they don't fund it. But ours was completely different. We used Unreal Engine, but I was like really customizing the Unreal Engine a lot, because we had our own rendering stack, like not fully, like we used their rendering, like their lighting pipelines and so on, but and post-processing pipelines as well, but the distance field rendering ray tracing tech in the beginning of the frame, which we wrote to their G buffers, it was completely our own technology, and of course the shadow map technology on this as well. And this actually brings me like one memory, like one of the first, like I wrote a really quick prototype when I was still working at Ubisoft, like one weekend prototype at home. Like if you know the shader toy, like shader toy has a lot of these distance field field like rendering prototypes, and they are usually like analytic distance fields, like not like the playbook is volumetric data structure. It's like similar to voxels, but you use volume textures and you store the distant values there. But on ShaderToy, you have analytic distance functions. You put basically the whole scene in a one function, and you are evaluating the whole scene for every iteration, which makes them really slow. But our tech has to be running at Nintendo Switch 1 and 60 frames per second on Xbox One and PlayStation 4, and also 4K 60 frames per second on PlayStation 4 Pro. So yeah, it had to be much faster than shader toys, of course. So we kind of take the distance functions to these volume textures in a sparse way. So that's why it runs so well. But the nice thing is that I wrote this 1 week prototype, and there was no sparse distance functions or anything like that. I was just writing with analytic functions and trying to make the shadow mapping work. And I got some really nice soft shadows with penumbra widening shadows and so on. And I was like, yeah, I just wrote this in 1 weekend. Like, this is what we should be doing. And at Ubisoft, we were doing the GPU-driven rendering tech, all the virtual shadow mapping. The virtual shadow mapping took like half a year for one engineer to implement, for example. Like, Nanite has virtual shadow mapping as well, but it's really complicated. And it's like added complications on top of the GPU-driven rendering as well. So we had virtual shadow mapping also back then. And I was like, this distance field thing, like this distance field ray tracing shadows, they are just like so much nicer than virtual shadow mapping. I implemented it in 1 day and it runs faster and looks better. And I'm like, yeah, let's go. Like, it was kind of like for me, like these technical things that I see that, okay, we can implement this. I cannot go to my own studio and I spent half a year implementing shadow maps. Of course I cannot do that. But if like, distance field, like this is nice. We don't need to care about triangles or any of the hard stuff. We just do this and we get the tech running in a short time, and we got the tech running in a short time. So it was really nice because I thought the tech is nice and interesting, and Media Molecule Dreams like also was doing a kind of similar thing, and that's like that was kind of one of the reasons why I left, that we had interesting tech that was not like triangle tech. It was not compatible with any existing asset pipelines. You couldn't bring triangle assets to distance field games. So we could do this on our own, and we were doing, because distance fields are like smooth surface, so we were doing clay simulation game of obviously on that because it suited the technology. So it was kind of really technology heavy project. Like we were like, even in the beginning, like it was just done for the tech, and this was one of the things like in a hindsight, like Sami, like when he left the company, he wanted to do good art and art style and tech art and so on. And of course, a good game. For me, it was like, oh yeah, I want to do my tech. And of course, like when people want different things in a small company, then it's like sometimes you have arguments and sometimes it doesn't go, and then your money is running out, and that kind of adds the stress and so on. But we were together 3 years and did that, and we were both like perfectionists in our areas also. But the game was quite well received. We managed to ship it on like 2-person team, Xbox, PlayStation, Nintendo Switch, also PC launch. So 4 platforms with 2 guys. The main thing that was like super heavy on the project, like in addition to the money and just having 2 persons and no game designer at all, was launching on consoles, like going through the certifications, like all of these platforms. Nowadays they are slightly bit less involving, but back in the day, like you had these kind of certification checklists. You had like thousands of different items that you have to fill. You have to test the game. You have to test the game, like take batteries out of the controller while you are entering network play, or do stuff like that, and plug in the cable and like everything, like all the random stuff that was really, like the testing was really heavy, and you had to ship it. You have to configure servers on Xbox. On PlayStation back in the day, you had to ship separately on Asia, EU and USA, and they were 3 different projects, 3 different, like you had to send the game 3 times, configure servers 3 times,
What?
like put the whole process 3 times, and it was different processes with different, like there was different websites, different publishing processes, everything, and we had a 2-person company, and it was like half a year to do all of the consoles. Nintendo, I think they had I don't remember, did they have a separate like Asia and everything else back then? Maybe they had, because they are Japanese companies, so the Asian market is different. So many are releasing like a slightly different version of the game as well on the Asian markets. And back in the day, localizations were big on like memory budget and so on. Nowadays, you just ship the same build. But yeah, you were shipping different games, and it took like half a year on our time to just publish it on all of those platforms, get past the certifications and configure it and ship it, and all the marketing material separately on every region, and of course localization. Like you have to localize console games. There are like 10 different languages or so that you have to localize and test and everything, and of course like they find issues, and because we were using some localization company to do the localization, but they were not matching the guidelines. On some console you have to translate the controller in so certain way, or player in certain way, or friend in certain way, and if you use a slightly bit different translation in some sentence, they will fail you, and if it crashes one time, you don't ship it, and it's a heavy process, especially for a two-person team, and that's why you have QA engineers. The QA engineers are like handling this. They are just doing that and nothing else. But we had to do it because there was nobody else to do it, and this is why, like, if anybody, like any indie devs are listening to it, like ship it on Steam first, or iPhone or Android, because they have really lightweight processes. They just basically just start the game and okay, it runs, it doesn't crash, like ship it, and you can ship it, and it's easy. But on consoles, it's so much work, especially if you are multi-platform on all the consoles. And we also made a really interesting mistake, or not a mistake, but we had
Technical
user-created
decision.
content, like always. Like we had a game, like you could create your own levels, the clay levels and everything, and we had level sharing, we had a server, but we wanted to make cross-platform level sharing between all of the consoles. Back in that day, like 7-8 years ago, and Microsoft had just like Sony and Microsoft had, like, there was one big AAA game, I don't remember the name, like somebody managed to negotiate with all of the console vendors that we are making a cross-platform something. I don't remember what was it, like was the cross-platform multiplayer or something. It was, console vendors never wanted that. They wanted their own ecosystems and everything, and we had user-created content platform that was sharing all the content between those. And of course, you could do the penises and everything, like all that stuff, like how we can handle all of these takedown requests and everything, and the server security, and like all of these documents that we had to provide to anybody, and they were like, when we were shipping the game, we were actually sending two bills, one with that disabled and one with that enabled for every vendor. And luckily for us, everybody shipped the version with user created content. So we had cross-platform user created content. Like it was, they were like internally, we never even knew that are they going to, like, because they had internal struggle whether they want this or not. And they were kind of opening it to big AAA games, like some Ubisoft games or stuff like that they could trust on, like, okay, this publisher is going to handle it well way. But we were accepted and shipped it with user created content, and it was pretty nice. So it was another kind of user created content platform, because I've always been doing those. And then when our money was running out, because I was talking about the Playbook at GDC and about the technology, and there was the ray tracing technology and the distance fields and GPU physics simulation, and at that point, like, ray tracing was heavy, and we were kind of demoing on AMD, like AMD was flying me there and so on, because it was running ray tracing on computers, not using ray tracing cores like NVIDIA, because they didn't have those yet. So they were, of course, promoting all ray tracing without ray tracing units. So I got to fly there and show that how well it runs on Vega 64 and of course on AMD-based consoles, and they were paying me the hotels and flights and everything, and it was nice for an indie company and talking about the tech. And of course I got more visibility because of ray tracing was starting to be cool then, and distance field, like everybody was starting to use distance field for lighting, like Lumen is using distance fields as well, and Unreal was using, and and not many big companies were starting to use distance field for all kind of stuff. So it was again cool tech at the right time, like the GPU-driven rendering a few years earlier, and when the money was running out, I had contacts with Epic, like because we were using Unreal Engine, I was submitting our engine optimization to them directly, and we actually got like 50,000 for them because I was optimizing the engine and the Xbox and PlayStation backends and so on the rendering backends. So I got money back from them. Like it was a nice way to fund the company as well. But of course, it took some of our time because their engine was not really, especially on Xbox, it was not ready. They were making a game called Paragon back then, and it was only on PlayStation. It was before Fortnite shipped. And when they started making Fortnite and shipping it, Fortnite was cross-platform, so that improved the Xbox platform backends a lot. But before that, we had to do a lot of work to make the Xbox workable, and I was shipping a lot of fixes on Xbox to them, and that got us money. And of course, we had to do the work because it was really not working. It was really slow, and it was even crashing and not allocating the ED. Like Xbox consoles have the ED-RAM scratchpad pool. You have to manage it really carefully because they have lower bandwidth on Microsoft Xbox 360 and Xbox One. Both had this kind of design that you had this small, fast memory scratchpad that you had to manually manage. A little bit like nowadays they have these Infinity caches on AMD, but kind of similar thing, but you had to manually kind of copy and allocate resources there. So you had to code for that. And Unreal 4.8 or 9 or 10 or whatever, I don't remember the exact number, it didn't really support that at all. So it was really slow on Xbox, and computers were super slow on PlayStation. They were kind of just, everything was using the cache coherency protocol. They were kind of allocating it in a way that it didn't use the fastest memory bus at all. But they didn't use computers that much back in the day in their games, so they didn't even notice those issues. But of course, we were using like just computers basically, like it was just compute pipeline and then combining with Unreal Engine G-Buffer. So we were noticing those issues. So of course I was pushing fixes to Unreal all the time, and like they were happy about that, and that's why I got like a lot of contacts with them. And of course, when they knew that our money was running out, they wanted to hire me, and they of course knew that I was writing the GPU-driven rendering technology. We were talking with them on a conference, and they were starting to write Nanite at that point. And they knew that I was like at Ubisoft, like I wrote their Nanite before, like that similar technology. So they of course wanted to hire me, and I was discussing with them, but I was also like they didn't have an office in Finland back then. They actually had an office like half a year later, but not at that point. And then I had some friends in gaming industry, like we were discussing, and they said that like you should kind of talk with other people as well. And I had AMD contacts, so I was talking with AMD as well, and they gave me offer, and also like Epic gave me an offer, but then I was talking with some like somebody introduced me. I think it was from Remedy. I think somebody from Remedy was introducing me to Natasha from Unity, like Natasha Tatarsuk. She's running SIGGRAPH's like real-time graphics rendering track every year, like the biggest like game rendering track on SIGGRAPH. And she was at Unity at that point. They just hired him and her, and they hired like Sebastian Lagarde and many other like really big names to do the HDRB rendering technology that they were just building. And then like I was talking to Natasha, and she wanted to hire me as well, and then we had discussions, and I ended up going to Unity at the end because Unity had an office in Finland. They had really nice office, really nice like working conditions. They knew kind of the Finnish working conditions, and at Epic, because they was a US-based company back then. It's kind of difficult to work in a US-based company if you are in Finland, because in Finland we have really long summer vacations, like we are month away, like we have like 6 weeks or 5 weeks summer vacation and long winter vacations and everything. Like, yeah, we have a lot of vacations. So then if you are in a US-based company, like everybody's always asking, like,
Yeah.
you are leaving, and now like it's a problem. But of course, I didn't know that they are going to have a Finnish office, and I didn't discuss with them that could I build my team in Finland or something like that. But at Unity, they were really open that they wanted me to build a team in Finland in the same time zone. They had back then they just had moved their headquarters to US, but they had still like their biggest studio was in Copenhagen, their old headquarters. So they had a lot of people in Finnish time zone. Also, like the HDRP team was in France. So it was for me, it was a kind of good place to work in the same time zone. So I choose Unity. I got really nice salary on them, and also I kind of like I didn't know. Of course, nobody know that Unity was going to IPO soon because you cannot like those are company secrets. So I got some stock, and the nice thing is that then like the stock completely skyrocket like because of the metaverse craze. Like everybody wanted to be metaverse, and the Unity stock was like just on the IPO it was doubling or tripling the stock, and I got pretty nice. Like when I sold my stock, I was just there for 2 years. I got paid half of our mortgage back on the house. So it was a really good like coincidence to kind of get there and get the money because it was like a jackpot for me because I was just coming from the second order and our money was running out,
Yeah,
and
yeah,
we
yeah.
were kind of like I was like optimizing the salaries. We were really low, like really low salaries, like basically half or like one third of like what normal people get, just so that we can just manage to live. And we had just had a new like our first, like our son was born at that point, and we had quite expensive like loan, and it was kind of struggle also at second order because the money was running out, and Sami, um, who didn't like have kids, he was a few years older, a few years younger than me, and he was still living as a rental apartment and so on. He didn't have this much like
Pressure.
financial like burden that I had, so it was kind of like also that was kind of a little bit iffy topic for us. Like if you are an indie company, you want to stretch the money, but like you cannot do it because then you cannot pay your loans or bills or whatever. And then like I joined Unity, and kind of the money problems went away immediately, or not immediately, but they were paying good salary, and then the IPO was complete like bonus for me. Like I didn't know, I was not like trying to optimize that Unity is going IPO. There was no discussions about that. So nobody knew about that, and suddenly they just announced that we are going IPO, and it was like a few months later, and the IPO started. So it was really quick. And for me, like the Unity was both good and bad. In the beginning, it was really nice because I was working a lot with Natasha, and not initially with Natasha. I was working with Natasha later, but initially I was like tasked to do the dots rendering technology. Like they had the new data-oriented tech stack called dots,
Yes.
and they needed rendering technology for that, so that the big ECS scenes could be rendered. And I was like, they had Mike Acton and some other big names like hired to do the ECS technology, and but they didn't have any rendering engineers. They were just like normal like engine programs wrote the rendering code for that. So it was really like maybe not the best rendering code ever, but
Yeah.
it was rendering a lot of objects. So we were like improving that stack and improving the Unity's rendering backend so that it can integrate better with the dots. So that we added like this kind of new rendering API that can batch render a lot of these things fast. We can just bring directly like big arrays of stuff and just push it through the whole Unity pipeline and just render it. Because Unity had this like really old rendering stack at that point. Maybe they have it still. I don't know. But it was slow. It was really slow. It was managed C# game objects running in a single thread, communicating with C++ and C Sharp, and all of that was not really good enough for Dots, because Dots was building this kind of demo called Megacity. It had 6 million entities. It was a really big, like, futuristic scene, and we needed to have a good rendering tech for that. So I was tasked to do that with the team, and we were building it together, and that technology allowed the Dots to kind of directly push a lot of data through the whole Unity thing in a way that it was kind of sidestepping all the slowness so that it could be directly rendered. So it was kind of a big batch, like this kind of big batch on the render graph that was just going through, like no processing at all, and then being expanded and rendered, like all the arrays and pointers and so on. It was like really that way. So we kind of sidestepped the whole the ugly thing. And they had their new, like, burst C# compiler back then. It was like this kind of C style subset of C#, like a specific, like, C# version that had limited C# functionality and no garbage collection, and it was really designed to be vectorized. The burst had this kind of burst jobs. We were basically like a little bit like compute kernels, but running on CPU cores, and they were fully, like, threading everything, and we were writing the whole rendering stack on top of that. And there was some calling callbacks, and it was just wide all cores and everything. I had 64 core Threadripper back then, 128 threads, and it was just scaling the whole system. So it was really nice to see, like, all the cores being lit. So yeah, it was kind of nice technology. We managed to render the Megacity really fast. It was like rendering like 200 times faster than the Unity's normal rendering pipeline or something, and that allowed the Dots to ship the thing. And Joachim was happy. Joachim was the CTO of the company. I was talking with him a lot. All the tech stuff. We of course at Ubisoft we had similar kind of ECS data structures. I was always, like, sharing ideas with him, like how to make the DOS better and what we need for rendering, and it was really nice doing that. And it turned out that this pipeline, or this kind of API that we managed to do, the batch rendering API, it was eventually, like, after I left the company, they are now kind of pushing all the rendering stuff through that. So Unity is basically rendering everything nowadays through the hole that we created, because it was so much faster. And not everything, not like skinned, like complex skinned objects or stuff like that, or like whatever. But the normal rendering, like normal mesh renders, all go through that path. And this was because we had these Hack Week projects. Like Unity had this really nice thing every summer happening. There was 1 week everybody was flying to, like, there was a kind of resort outside Copenhagen that could host like 700 people. There was swimming pools and everything, and beach, and people were just bringing their laptops and coding, and there was always drinks and food and everything, and late night parties and whatever. And we were just like, everybody had to be in a team. You had to join a team. Like, it was also like a mixing event that everybody knows each other in the company. So we were forming teams, and we were doing this DOS rendering prototype in one of these Hack Weeks, which is like what I was talking about earlier. We had really nice team, and that kind of team, like most of those people become the DOS rendering team. And like 1 year earlier, like people have kickstarted the Unity URP and HDRP and all of those things. Nowadays, those pipelines like HDRP is pretty much dead, and URP is now the only pipeline there. And finally, they are killing the old pipeline as well. But everything takes time. Like Unity is a big company. It was like 5,000 people when I left, so a lot of people. And when I joined, it was only like half of that. So there was a lot of growing pains, a lot of like organization restructures, a lot of these. I think like when they were going through the IPO, they tried to kind of bloat the company. The CEO back then was like a business person. It wasn't like Tim Sweeney. Tim Sweeney knows tech, and he knows like games. He's a gamer, like he knows games, he knows game engines, he uses the tool all the time, he writes code himself. But Unity CEO was a businessman. He was really good at getting investors and bloating the company value for the IPO, and that's it. And this was kind of good for the IPO, good for people to get money, but they should have changed the CEO after the IPO. But I guess because the IPO was so successful, like financially, they didn't want to change the CEO because the company was so bloated and there was so much like Unity tried to do everything. They bought the Veta Digital, which was the movie company behind Avatar and behind like the Lord of the Rings, of course. I was always talking about like the Minas Tirith battle. Like that was always like when people were asking like why we need this tech. Like I say, like okay, we need to run the Minas Tirith battle at real time. Like all of those things. Like it needs to be dynamic. It just cannot be a static scene. It needs to be like a real thing. That's why we need dots and so on. But there is always a struggle at Unity. Like some part of the Unity, like the traditionally Unity was like mobile games only, and they are still like I think they still own like 50% of the mobile games market. So it was really big market for them, even bigger than if I remember correctly. So it was always a struggle, like these new technologies like HDRP and dots, because many of these people thought that Unity should become more like Adobe, like really easy to do, like really polished tools, like uh, they didn't want to make it any more difficult. It should be less difficult. Add like all of these like visual node graphs, like Unity had this, and Unreal had this blueprint
Shader graph.
node graph,
Yeah.
and they wanted similar thing and shader graphs and so on. Like everything, nothing should be code anymore. And they thought that it would be that and the metaverse thing, and everybody is doing these node graphs and so on. And and then like that's one of the reasons why dots didn't really get traction. But Unity's like core technology was so old and slow and so on. So it was completely impossible to run these movie scenes. Like if you would imagine like Minas Tirith battle running on a like emulated C# code in a single thread, like it's not what works. Like if you need the dots technology and everything that scales up. And you also need like nano style rendering, and that's something that I started doing at Unity. Like I had my own team like after the dots team, and there was struggles with dots and the priorities were always shifting. And even the CTO Joachim was like he is no longer the CTO. Like yeah, so much like political struggle inside the company, and of course growing pains because it was doubling, and suddenly like a lot of firing people as well on the other side. And um, not the easy place to work in the last years. And I was trying to do the GPU driven rendering technology, but people thought it's one of those like non-mobile technologies, like it's enabling us to run these big movies maybe because like if you look at the other side of the fence, like what Epic was doing, they built a nanite and all of the technology stack in like just like 3 years, the same way time I was actually at Unity. And nanite is like a symbiosis of like 7 massive systems together. But Tim Sweeney is like he knows how to kind of steer the boat. Like he knows like, we want to go to movies, we want to go this and there, and he has a lot of good technical persons like right next to him, and he trusts them. And uh, they kind of knew like they want to go here, and they made it the kind of the whole company is going that way. But at Unity, like it was like most of the company was like, yeah, we want to go mobile only, these new stuff, we don't care. But then we bought this movie company. But like yeah, it's like sometimes I was just joking, like this is just joking, like you get like real-time game engine, and then you have movies, and then you get real-time movies when you combine. And that's what like if you take a manager and he thinks like, yeah, let's combine these together, and then you have real-time movies. But it doesn't work like that, because like movie code, like their offline rendering tech, it needs to be like 100 or maybe 1,000 times faster than what it is to make be usable in real-time code. So it's an optimization problem, it's a really technical problem. You need to you need to make the data structures really efficient. And when you try to load these scenes, like the Disney Moana scene or whatever scene to Unity, the whole thing, like it will freeze for a really long time and then will crash. So yeah, it's like the editor, everything, and I managed to load some scene, and I was clicking objects, and it was like 5 seconds stall every time I click on an object, and I'm like, yeah, this is not usable. Like, it's not just runtime stack, but it's editor stack and everything. Like, if you need to run these movies, it's like the whole tech stack needs to be super optimized. The editor needs to be super optimized. And actually, the dot stack was doing that because it was kind of keeping only a really small part, like the objects that you were editing at the moment, as game objects, because the editor was communicating with game objects. It didn't communicate with dots. So the dots was like runtime converting the game objects to like change game objects and their components to dots representation. And most of the scene was rendering with the dots, and it was really fast. And you could actually navigate these like 2 million entity scenes, like 2 million, like they were actually like the editor made it look like you had 6 million like game objects there, but you didn't actually. You just have a few that you were editing, but it was a good illusion, and it was working. It was real time updating everything, and that made it work. But there was simply no like. There was no consensus that there was not enough people behind that dots is going to be the new stack, and we are going to rewrite the whole Unity core to be dots. So it was a struggle, and I was also like in the center of the struggle, and especially when we started doing the GPU-driven rendering, and I was doing the prototype, and we had like this kind of nanite-style V-buffer rendering, everything running on Unity. It was really fast. Of course, it was a prototype, it didn't support everything. It was not in a shippable quality. I was doing it with one extra guy. So that's the resourcing, amount of resources you put. Like, these guys have this nanite and lumen and everything, and we have a couple of guys doing something similar, because it's not like a huge priority for Unity. But then, like, yeah, we try to like talk about with other teams, like how we can land it, and it's like way too much politics to kind of like, because it's kind of, if you want to have this kind of nanite style tech, it affects the whole asset pipeline. It affects everything, streaming and console backends and everything. Like, you have to have everybody on board, and everybody was not on board. So I was kind of at that point like yeah, we cannot land it. Like, it's like we are just wasting the work, and talking to Natasha and being like depressed on that, and and then like the interesting thing is that it was kind of a hard year for me but I was talked to like the HypeHype CEO, like I think he was talking to me like on the Christmas vacation, I guess. And my father also said that I'm so tired, and we had a lot of like late night meetings as well back in the day, because there was so much politics. Like, I had to convince some big managers that we want to move there. And of course, like, I was at that time I was directly on Natasha's team, which was a US based team, so we had a lot of US based contacts because it was on their time zone. So I was lot of like late night meetings starting at 8 p.m. or 9 p.m. and so on. And my father said, like, you are so tired, and I was like, yeah, I'm really stressed out, and I couldn't land the code. And yeah, it was so nice to do the prototype. Like, we can do it. I have my own hack week to just kickstart the project and so on. But it was so difficult, and then I just like, yeah, maybe I go to a company where I can actually land my code. Like, it's like, because at that point they just bought a massive like movie company, and somebody has to make the tech so that you can actually make those things run. So yeah, I don't know like what was the plan. Like, apparently there was no real plan. Like, people didn't want to embrace dots, and they didn't want to embrace the GPU render or any of these advanced technologies that were required. And of course, like, after that I left, but there was a lot of Natasha left, Sebastian Lagarde left, like basically everybody in the HDRP team left, and all of these teams. Of course, there was some firing as well, like rest of the people were fired because we didn't want to focus anymore on those areas. But yeah, it's like, I would like it was a good move for them right now to kind of move to a one pipeline, because Epic has been always having one pipeline. Of course, they have a mobile version and a desktop version of that, but they are kind of the same pipeline, but you have a different shader configuration. You can configure the shaders differently. There are different if devs. It's kind of the same ecosystem. But on Unity, you had HDRP and URP, and they're completely separate ecosystems in a way that you have incompatible materials, incompatible shaders.
And you have
If
built
you
in,
make your
and you have
game for
built in,
HDRP,
right?
you could not port to URP. You couldn't ship I want to ship high-end PC on HDRP and console on or mobile on URP. That was completely impossible. You could make completely different assets, and the whole asset store was super nice for Unity. All the assets were compatible, but now you had to make 3 different versions of the asset, for built-in render pipeline, URP and HDRP, and it just felt to me that there was kind of nobody on the top who was saying that, okay, we need to think about all of these things. Asset storage is important, compatibility is important, these things are important. And when they started buying these other companies in the metaverse craze, it was even more like that. Nobody was coordinating the show. So it was kind of difficult for me. And I knew that the tech would just be thrown away. So I just yeah, I get good salary, but I just want to ship the tech. I want people to use my code and so on. And so then I left at HypeHype. I was yeah, okay. And I called back to Johannes and yeah, I'm now ready. He has been trying to hire me several times because they had a small startup doing the HypeHype for a couple of years before. And I always said, no, I'm happy at Unity, but at that point I was okay, let's do it.
Can you do an overview of HypeHype? What is the mission of the company?
Yeah, that's kind of interesting thing because actually the product got canned a couple of weeks ago, but we are building a new product now. But yeah, let's start what it was back then. They were a company called Frogmind back in the day. They were doing mobile games, Android, iOS, and they were actually quite successful. And they were half owned by Supercell, the biggest Finnish game company right now. They are mostly they are. I think they have big owners like Tencent and so on. So Supercell is a big company, and they were only half of HypeHype. Nowadays, HypeHype has more investors as well. There is no majority owner, but back then, Supercell was really kind of owning the HypeHype, and they got a big investment from Supercell, and now there's even more investor money. And the idea for HypeHype was to create a TikTok of games. TikTok was important then, and it was kind of a feed. You had mobile phone feed, you are scrolling the feed, and you see these small videos, 10-second videos. It was a brand new thing, skyrocketing back then. As you know, was it 5 years ago, 6 years ago? And of course, now there has been controversy as well because it's so popular that people are shutting it down, and because it's Chinese, of course. But the thing with that was that it was really hot back then, and this kind of mobile game development wasn't really started. So it was kind of at the same time, it was TikTok of games. You could scroll the game, they would instant load. You could create the games on your mobile phone. Unlike Roblox, in Roblox, you have to download a PC client. So it's only semi-professional creators do it because they have to own a PC and install the tools and just use keyboard and mouse and so on. But HypeHype was that you could create everything on your touchscreen, on your phone or tablet. And it was kind of this, and the games were instant loading and easier to discover. You didn't need to load it. So it was kind of this kind of a little bit more modern version of Roblox back in the day. But the thing, of course, is that if you want to do a new kind of this social gaming platform, Roblox had a lot of people. They had their friends there and so on. Even if you have a platform that could technically be better in certain areas, it is really difficult to get the customers to move. And especially for user-created content, if you don't have a massive pool of people, you don't the best basically the pool of people is dictating how big your iceberg is, what is the size of the top creators. And the top creators are of course making all of the top 100, top 20 games and nobody's playing anything else.
Yes.
So it's like on every platform, it's like only the top games get played. Like nothing else is, like everything else is visible. And it's almost the same on Steam as well. Like if you look at top 100 list, like it's basically 99% of all the sales, or even top 10 is like 90% or something, but it's like nobody else gets any visibility. But we didn't have enough good quality creators to create really good games on the platform. We had massive amount of really shitty games, like almost 500,000 games on the platform in the end. So yeah, there's a lot of these small games. And it was first created to be like a hyper casual platform. Back in the day, hyper casual games were also like one thing that was super big. Like some of the companies were even making massive money with these small hyper casual games. They were also like click once, you have like a bouncing ball or whatever, and you're clicking and doing and swiping and whatever. A lot of these kind of games. And HypeHype was like, yeah, let's make this game that is TikTok with hyper casual games, and you can create the games instantly on the platform on a touchscreen. So it's like super nice. And the idea was good, but of course, if you don't have enough good games, then people don't play it, and if you don't have your friends on the platform, you don't go there and so on. So the platform didn't really live up to the expectations. And and one of the, I would say one of the failures was also that we had touchscreen editor, but it was a node graph based editor, but the node graph was like for these people who play mobile games, they want to make game on their really small device. It's super hard to fit a good node graph on the screen. So it was really messy to make those games. So the experience was even worse than when you use Unity or something. So you need kind of more patience, and I would say that you need roughly the same amount of skill that make a Unity or Roblox game. So even though we had the touchscreen there, basically allowing people to do games on their phone, only a really small amount of people were capable of doing that. And those same guys who were actually capable of doing it, they used tablet or they used a PC client. So there was not really... There was a PC client as well, we shipped it later, because the creators wanted a PC client. So basically like 90% of the good games were made on PC or iPad anyway, because the phone screen was so small, it was really hard to make productive content on that. Like, of course, phones have been growing all the time, so it's slightly bit easier now. But their phones were smaller 5 years ago, so yeah. And well, actually the platform was killed like a couple of weeks ago, so I cannot blame the phones of 5 years old, but it was that time, it was designed for that kind of audiences, that kind of thing, what was popular back then. But after that, like we all knew that like social game platforms like Minecraft of course was popular even back then, but Fortnite has become more popular, and of course Roblox also, like they have like a lot of social events there and everything. So for social platforms, it's really important that you are clearly better than all of the competitors. Otherwise, you cannot get their customers because their friends are on the platform. So it's really hard to kind of compete. If you want to be better, Facebook or like Threads was like, I don't know, like Twitter, and there's a lot of competitors trying to beat Twitter, but it's difficult because everybody is on Twitter. So kind of the same problem. So HypeHype never kind of get like the snowball rolling really. There was good amount of people, but it was kind of more like that you could have a small like 20 people company running it, and it would be fine for that. But we had back in the day, like we had like 60 people working on the platform, so it was bleeding money, and of course like investors wanted us to start focusing on AI. So that's the thing that what we are doing right now. I cannot. Maybe I can talk about that next month or something. We have some really nice prototypes running on that, but it's not public yet. But I'm allowed to say that we are working on AI stuff. So of course, yeah, if games are hard to make for people, then you can just use AI tools and make it easier for them to do it. So that's something that we are researching right now, but I cannot say any timelines right now. Like it's a prototype product. So, but
On the technical level, how does the tech differs from what you've been doing back in the day, even like at Ubisoft, the GPU rendering, now compared to HypeHype, where you need to target the mobile?
yeah, that's a really interesting question. On mobile, you would say that the GPUs are roughly like the technology or the architecture is maybe like 5 years behind. Not on Apple anymore because Apple has super high end, like they have been hiring, they have so much money, they have been hiring like a lot of experts from Nvidia and AMD and other companies. And they have like they're like M1 and M2 and so on. Those MacBooks have really good technology, and the GPUs are really good as well, and and they have the same architecture on their phones. So Apple devices they have really like advanced GPUs that could do GPU driven rendering. They can write like you can write a computer on Apple device, write commands to command buffer and everything. Like they have super nice binders nowadays. Like pretty much like anything I would like. There's a couple of API hitches that I mentioned in my blog post that I would like to be fixed about like the descriptor indexing and so on. But once those are fixed, they are just software issues, like not hardware issues. Once those are fixed, then I would say that Metal is kind of the best API at that point. Of course, the problem is that Metal is limited to one platform, so you cannot really lean on Metal. So so on mobile, you have to do tech that runs on Android, and Android is a much worse case for anything. There are multiple reasons. The first reason is that Apple is only shipping high-end devices, high-end premium devices. So if you look like 11 years old iPhone 6s, which was like their first 2 GB phone, which was our min spec for a really long time, it's 11 years old phone. Basically, it was the min spec all the time for us. That phone still had a GPU that is as fast as nowadays. If you buy the cheapest Android phone today, which is like less than 100 euros, if you buy that kind of phone, you have the same GPU performance that you had on iPhone like 10 years ago. But the iPhone was, of course, the most expensive phone that you could buy at that point. And this Android phone is the cheapest possible phone that you can buy. But HypeHype customers, of course, if you think about these social gaming platforms that run on your phone, like the 10 years old kids play that, 15 years old kids play
Exactly.
those, like even 8 years old kids play those, like on first class. So they have their parents' old phones. Like parents use their phone for 4 years, they give it to their kid who uses them for 4 years. So they are normally like quite old phones. And it's not really a problem if you think about like USA or Finland or Europe, because our parents buy expensive phones. But if you think about Philippines, their parents buy like this 100 euro, like cheapest Android shit you can ever find, and then 4 years later they give it to their kid, and then like couple of years after that they play HypeHype with that. So it's like these shitty phones, but you take them like 6 years old shitty phones, and those are really crappy. So those are like 5 times slower. Like when we were doing like most of the time at HypeHype, those were like 5 times slower than the iPhone 6s. So basically like 5 times slower than a 10 years old
Wow.
iPhone on a GPU front. They had like 8 core CPUs, but 8 really slow. They only put like this slowest, crappiest cores, but they put 8 of them for marketing purposes. So you can say 8 core CPU. So you have 8 slow cores instead of
One
like
single.
Apple had like 2 fast cores, and one of these Apple cores were faster than all of these 8 cores combined. So, but Apple had like 2 of them. So it's kind of easier to write, and Apple is making really good hardware. But of course, on high end, like if you buy a Samsung phone, they have 7 years of software support, and if you buy the flagship phone, like 1,000 euro phone, then it's a fine phone. Like it's a good phone. It's got a lot of support. But these cheap Chinese phones, they have only like 2 years of software support. So they didn't get new Vulkan drivers. They had really crappy old
Oh.
drivers with a lot of bugs and so on. So So the biggest problem was that at some point, because we wanted to land our Vulkan renderer because it was giving us really big performance boost, because I rewrote the whole rendering stack. When I joined HypeHype, the first year I spent like rewriting the whole platform specific rendering code that they had got them from their old like mobile game projects, and there was even some BlackBerry code there left, so it was like really old code base. But I was kind of rewriting that stuff, the whole rendering code, and it became really fast. I was talking at Seacraft 2 times in a row about the architecture of that thing, and there was a really good CPU architecture, really fast architecture, really like designed for Vulkan and Metal 2 actually. And because Metal 2 is like on iPhone 6 as you have Metal 2, so that was our min spec. We didn't fortunately have to support older Metal versions. And then we were also designing it from the ground up to Web GPU. Web GPU wasn't launched back then, but at Unity I was giving Web GPU team feedback also on the design. There was one of the guys who was working in Finland in the office. He was Unity's like Web GPU guy, like who was giving Web GPU feedback, and he was asking me like low level technical feedback about the spec, so I knew the spec really well. So when we designed our own internal like graphics API, it was quite similar to Web GPU, except that we could support persistently mapped GPU memory, which is a really big difference, because then you can write directly to GPU memory in your on like you can just map GPU pointers and directly write to GPU memory, which makes things faster because you don't need to copy things around. And it also reduces like the GPU overhead, like a driver overhead in a way. And there was a couple of other like important things that we had on our API compared to Web GPU, and this was one of the like how would I say it? I have been asked many times like why we didn't use like Molten VK on Apple devices to just port our web like Vulkan code directly run it on Apple, but our raw code was so efficient. It was written for Metal 2. Back then Molten VK was only using Metal 1, and Metal 1 has this kind of DirectX 11 style like binding model where you're binding every resource separately, and on Metal 2, you can combine them to argument buffers in the same way that you have on Vulkan and Web GPU. So you are kind of pre-creating your bindings, and then you can just easily switch material with one kind of command. So this made our rendering pipeline, like our native rendering pipeline, like 40% faster than Molten VK on Apple devices. So it was a good time investment to write our own Metal 2 backend. We were also, of course, faster than Web GPU. Some people use Web GPU nowadays on desktop as well, because then you just write the code once and you can run it on everywhere. But the same thing applies. Web GPU is a little bit better than Molten VK. So there's a little bit less overhead, but the data upload path is I don't like it. I really like writing data directly to GPU memory without any copies, because this allows you to do some things really nicely. So that's kind of the biggest issue I have with Web GPU. And there are some other issues like computers, for example. In Vulkan, you have full control about like how do you can just spawn multiple computers and run them in parallel, and then you do barrier and then you block the results. On Metal, you can do the same. You can do a parallel encoder, like compute encoder, and put it in a parallel mode. Then you can just run the dispatches at the same time. They don't block each other. Like otherwise, they would run one at a time. But on WebGPU, you have nothing like that. So if you have a lot of these small compute dispatches on WebGPU, you will get barriers between all of these. So it's slow. And this is something that actually, when we were working on the GPU-driven rendering back in the day, Ubisoft was asking Microsoft to add direct, like there was specific hacks on NVIDIA and AMD and Intel drivers that allow you to not put barriers between the compute dispatches. You can do this kind of, it was called UAV overlap or whatever. There was this kind of API backdoor that you could just say to the driver, don't put me barriers, and then you put the compute dispatches and then you put it back. And I don't remember how it was hacked in the API, but it was completely like black magic, and it just worked on the drivers, and then you could get better performance. On Playbook, like we had this kind of compute dispatches, and I had to kind of do the similar kind of optimization to Unreal Engine, and it was running some of these patches like 6 times faster with that because there was a lot of small compute dispatches, and now they could fill the GPU at the same time. So it's kind of important, and I hope that Web GPU is going to be fixing that. They will not allow us manual barriers, but at least give it the same thing that Metal has, that you can just put that this compute encoder has parallel execution enabled, and then you can just kind of group them together, and this is the group of things you can run at the same time. So this is kind of the other issue I have with Web GPU, and then yes, a lot of these small things, but I will write a blog post about the whole Web GPU issue. Like, of course, right now we are doing like really heavily Web GPU code, and Web GPU is going to be our main platform in the future. So for me, it's both really nice because now I can run computers on web and everything, because WebGL was really like it was basically like 20 years old DirectX 9 on web, and that was last fall. After the summer vacations, Apple added support for Web GPU in Safari officially, and before that, like all web graphics was DirectX 9. Basically, like WebGL2 is DirectX 9, so it's like 20 plus years old stuff. Like it's like basically the first really programmable GPU API. It's so old, and I'm really happy that we don't have to do it anymore. But Web GPU design is like 10 years old Vulkan 1, because Vulkan and Metal and DirectX are already 10 years old APIs. So now we get 10 years old stuff on the web. It's better than 20 years old stuff, of course, but it's still 10 years old. So yeah, that's kind of my main issue with that. And of course, like, yeah, you cannot write on a web browser when your rendering stack is running on different process, so that if the renderer crashes, your browser doesn't crash. So but I'm wanting that have a direct pointers to GPU memory, but that's of course like the security model, everything. Like, of course they will not give me that, but it would be nice to have it, and that's why we need a separate API for native applications, because this really makes data movement so much faster because you can directly write to GPU memory. So we definitely want that on native builds. So yeah, one of the reasons why we have a separate graphics API and not using some kind of wrapper directly like Web GPU or Molten VK or something like that. We just need our own thing.
So I want to talk about your huge blog post, no graphics API, and but then like we started kind of already alluding to some of the subjects there with the direct pointers to the GPU memory memory between CPU and GPU. Do you want to say something to close out the HypeHype part before we move into the blog post area?
Yeah, I would just want to say that when I discussed with the HypeHype CEO Johannes Vuorinen to join there, and he really respects me. He was actually part of there is a backstory of like why I joined that company. He was actually working on the editor at the Redlink studio when we were doing the Trials games. The first editor that allowed you to do all the first-person shooters inside the motorcycle game, and he was really impressed. Like we were creating like this user-created content platform even at that point, like just trying to make it was inside a motorcycle game. These were completely stupid, but we always wanted to do that, and he had the dream of making that, and then he made some successful mobile games. He left after that project like many years before me with one artist to create mobile games, and they had the dream of making like this user-created content platform, and we were trying later at Ubisoft to do that, but it was not really like Ubisoft style like thing to do. Of course, nowadays they have Trackmania and some other games as well, which do that pretty well. So Ubisoft also has success with user-created content. So it's not all of that, but we wanted to make that, they wanted to make that, and then like he was showing the prototype, and I was unhappy at Unity, so it was quite easy to convince me, and he gave me full hands, like I can completely rewrite the rendering backends and throw away all of the old shitty code. And at Unity, I never, like, there was never
Got
like
that
time and
permission.
place
Yeah.
to do that. And this company, much smaller company, smaller code base, of course, not like tens of thousands of customers. Like of course, at Unity it's a different thing because you have so many customers running in your engine all the time. It's really hard to just replace the backend code completely. Like it's not going to happen. So at this company it was easy. I was like Johannes was saying to me that you can completely talk openly about that in Twitter or anywhere you want. Of course, except like some kind of investor things, but or like product launch schedules and stuff like that. But I was like given full hands, and this is super important because I barely like it was really like when I was talking at SIGGRAPH, it was super important the GPU-driven rendering talk for my career. But it was almost that because the project was cancelled at some point, it could have been like the whole tech that could have been completely unpublished, like no trace at all. So it was really lucky for me that I was talking so much and collaborating with other Ubisoft teams, and their games were not cancelled, and we were talking together. So this is why I managed to talk about that. And I know a lot of people in game dev who have made like big projects with a lot of good tech, and the games have been cancelled. And then like they have like 5 years of tech or like 3 years of tech or so on, and tech might be amazing, but nobody has seen the tech and nobody knows about the tech because of course like game developer studios have a lot of high NDAs. So for me, it was super important if I'm taking the risk to go into a small company, I can continue building my brand in social media and talk about that. And like if the project get cancelled, then at least I get to talk about all the cool tech that I wrote. So that's kind of the thing.
You have a blog and you have one post there, and it's this
Yeah.
giant post. I think it was published a couple of months ago, I think,
Yeah. Just
right?
before Christmas.
Yeah. And it's titled No Graphics API. And it outlines like this like beautiful vision, like dreamlike
Yeah.
vision of like getting rid of most of the graphics API that we know and the troubles we like connect with graphics API, and replacing it with a simpler one. Can you I know it's a huge blog post and we can't really cover this in detail, but for everybody who is listening, sort of outline what's the main idea.
First of all, yes, it's a clickbait title. Of course, it will present you with a graphics API still, but the idea is that we could kind of get the main graphics API in like 100 lines or something, like not like 20,000 lines like Vulkan is, or like not 20,000 lines is Vulkan is much more than that, but yeah, it's kind of like the idea on the whole thing is that I have been wanting to talk about this since the Unity days. I have been writing like a lot of code on different APIs at HypeHype, even more, like struggling with the driver complexity issues, driver bugs, and so on. And the whole thing is that we have so many bugs because the drivers are so complex and they don't need to be that complex anymore. And the drivers are complex, but also it's so complex to use the APIs, and modern hardware doesn't need that kind of abstraction anymore. And 10 years ago, like when you had like Vulkan 1, DirectX 12 and 12.0 and Metal 1, you still had to support like 12, 13 years old hardware. So those APIs were designed in a way that those old GPUs could support that. And if we look at like what GPUs looked like 13 years ago, it was the first generations after we merged pixel and vertex shaders together and when we got compute shaders. So compute shaders were brand new. Pixel and vertex shaders were before that. So now you had a unified architecture that were running like one SIMD unit was running all the shader types. And And of course, this required a lot of changes on GPUs, like their cache architectures, everything, like everything need to be running coherently on these SIMD cores. Of course, caches were not fully coherent, but it was a big change. And of course, it was time to do a new API for those new architectures. Also, these new architectures have multiple queues, so you could push like a workload from multiple threads on them. So people wanted to be able to, because the CPU core counts were increasing a lot, and people had 4 cores or 8 cores or even 16 cores, and the consoles as well. So people wanted to bring this kind of console quality graphics to PC. In a way, like if I say console quality graphics, I mean that you can do cheap pro calls a lot, because console had really like the APIs were low level, but also you could drive the API from multiple threads. On PC, on OpenGL, on DirectX 11, you had basically single thread. On DirectX 11, there was a support for multiple threads, but it was really horrible, and all the driver manufacturers said don't use it because it just slows you down. So basically, single core and slow API, and they were designed in a way that the API was really flexible. You could just set up things. It was like OpenGL. Every state is separate. Every binding is separate, and it was made in a way so that it is kind of flexible to use, easy to use, and then the driver does all the magic. Driver combines everything, and then the way that all of these new APIs were designed, like Vulkan and DirectX especially, was that okay, now we have these small states. Let's put all of them together so that now, instead of configuring your pipeline or rendering pipeline, like in a pipeline, I mean like one shader basically, like shader, like pipeline in a way that there's a pixel and vertex shader separately, or maybe a compute like geometry shader or whatever. But this is like you combine them together, and now you have this big blob, which is called like pipeline state objects, and this is nicer for a driver because now the driver kind of like offline, like that was a startup, like when you are creating it once, it can then do the pipeline, combine the stages together, kind of make it so that it lives maybe in GPU memory directly or in a place that the driver can simply like read the data and just submit the draw call really simply. But this kind of like, it felt like it was a solution for this. Like you had this small grind state and then you had this massive state blob. So it was like the pendulum was swinging from this side to that side. Like let's make everything in a different way than before. But then people started like, yeah, but I want to dynamically select my blend state or stencil reference value or whatever. Like there was like, but this is so stupid. Like I cannot do these things dynamically anymore, and I want to tweak this value. I want to find a different texture or whatever, and everything was so rigid, and you had to compile like, yeah, but if you want to use this shader with 2 different blend states, you need to compile 2 versions of the pipeline state object with the same shader, identical shader code. Usually, of course, on mobile you can mix the blending equation to the shader code, but that's a different deal. But everything was combined together because maybe some hardware manufacturer on desktop or on mobile might use this state and optimize their share or maybe save one instruction or whatever. Then if you combine them all together, you get rid of the overhead on the driver and you get rid of the overhead on the shader. Or you don't need to compromise on that. And this kind of works in a way that if you are doing a small prototype or a small benchmark or whatever, like of course the vendors are prototyping with teams, like the 3D Mark, for example. It was one of the, like I mentioned it earlier, it was the Finnish company that made the benchmarking tool, and they had of course DirectX 12 and Vulkan benchmarks and all of that, and people were using, and their draw call benchmark, like yeah, it can draw something like, I don't remember, was it like 40,000 draw calls per frame or something at 60, or I don't remember the exact numbers, but it was really back then, and people were using, ooh, this is fast, and this is so much better than DirectX 11. If you run 3D Mark with DirectX 11, you only get a couple of thousand draw calls on the same scene. So people are thinking, oh, this is like 10 times faster. And it can be if you have really small amount of pipeline permutations and really like tuned render for that, and if you are really heavily draw call bound. Before you had like a single thread, and now you have multiple threads, and you have much cheaper draw calls because you have bound all the state together ahead of time. So you can see big numbers like that. But then in real games like Unity, Ubisoft, Epic, they had their DirectX 11 backends, DirectX 12 backends, and so on. And when they shipped, they were all slower than DirectX 11. It was like only a couple of percent, but for these companies, the priority was that we bring DirectX 12 because it gives us ray tracing or something like that. It's not about performance, and they just wanted the new features, and it was so difficult to fit these new APIs on the old rendering hardware interfaces. Like all of these big engines have a rendering hardware interface, which is basically your engine to rendering API. And they were designed for this old like DirectX 11 style rendering where you can bind every resource separately and you have separate blend states and you have separate like everything. And this just didn't fit. You could, and the reason why it's slow is that now under like you are treating the new API like it would be DirectX 11 still, but then you have a massive translation layer between, like a lot of hash maps and a lot of like hash maps are randomizing your memory access patterns because on purpose they kind of try to make it so that you don't have collisions. Like if people don't know the data structure, like you create a kind of big array and you kind of try to randomize the access patterns in a way that there's no collisions. But then if you use these hash maps rapidly, you will kind of randomize the access that you do on memory, and that like your CPU caches don't like it. So you will get a lot of cache misses, and today's CPU code is mostly like cache bound. Like processors do so many instructions nowadays on cycle, but memory has not increased. Memory speed has not increased as much. So nowadays, like good code is code that is reading memory linearly and optimizing caches. You can do a lot of instructions if you want, but really important is that the data structure is like local, like it is cache local and optimized for caches, and hash map is not good for that. And now of these backends, they were hash mapping everything, like all the states, everything. Like there are so many hash maps for the bindings, and you also had to combine the bindings on Vulkan. Like you had to ahead of time combine all of the bindings, the descriptors on Vulkan. On DirectX 12, it's slightly bit different, but people do that as well. They allocate like descriptable table ranges for combinations, and they just put it there. But now, because if you would want to build them every frame, you would need to do a lot of like basically API calls to the graphics API and do a lot of CPU GPU traffic to fill all of these things. So you are caching them and you are just putting them on the memory and kind of getting them back. But and the issue here is that it costs a lot of CPU cycles and you are doing a lot of tracking. You are also doing barrier tracking manually nowadays, which means that you need to remember the state of each resource. I was writing to this buffer and now I'm reading and I need to do this barrier here, and every resource needs to be tracked. So you need to do that as well manually. And it is faster, but all of these bookkeeping tasks are now on your responsibility. So you are doing that. And that made the backend slower. And those guys who were writing the backends, they are not NVIDIA driver engineers. So they, like NVIDIA has a lot of guys, they can optimize the backend. They have maybe a little bit more resources. Of course, like game engine developers are really performance oriented as well. They can write fast code, but if you have a company specialized on just that and they have been optimizing their drivers for like 10 years, then of course they can do a better job. They have more time to do that and more experience compared to like, this is a new API, write your own driver basically, and it is difficult. And to get around all of that, this whole thing was required because all of the GPUs back then had different binding models. You had to, like, CPU was the only thing to be able to bind stuff to the shader. So you had to kind of do this kind of ahead of time mappings so that your draw calls, like when you are drawing exactly, the draw call would be fast because all of the data mapping has been done ahead of time and cached somewhere, like it's persistent. So that way, like you can make the draw calls faster. But this means that because these are kind of retain mode objects, like you need to create these objects and keep them somewhere. but your rendering hardware interface assumes that everything is dynamic. I'm just giving these bindings, so you need to combine them, hash them together to find your persistent objects. So you have this kind of massive hash mapping mechanism, which is really slow as well. And then, of course, sometimes you have frames that the hash maps don't, like, they don't find what you are looking for, and then you need to create these resources. And especially if you are creating pipeline state objects, which are kind of the shader things. Like if you, oh, there's a new blend state, I never touched it, you need to create a new pipeline state object for that, which means that you need to compile the whole shader code at that point, because every pipeline state object has a copy of the whole shader code, even if you're only changing one blend state, because everything is combined. So that's why you have such a massive caches for these pipeline state objects. You have caches of them on RAM, you have caches on them on your hard disk, which can be like gigabytes, and then NVIDIA and Steam, they have cloud caches as well, because you have so many pipeline states, or you put in them in big cloud server so that people can share their pipeline state objects. So you can have like gigabytes of them in one game. So this is a problem. Like you have so much state, and because you have bundled everything together, you have created kind of this explosion of state, because every single toggle will double the state. Like if you have one extra state, then it's always twice as many. So this is a problem. And of course, like, this is why Unreal Engine games are stuttering and having all of these issues, and gamers don't like it anymore, because it's getting a bigger and bigger issue every year, because you have more complexities. So we have created this kind of unneeded dependency between all of the states and all of the inputs and all of the shader state together. And if anything changes, then we just need to compile a new variant, and it's not kind of good idea. And we should have, like, when we introduce a cloud server to cache those shader pipelines, we should have known that, okay, this is a bad idea. Like, we should fix the architecture at some point, like gigabytes of like different shader codes, like for one game. So it's not good. So that's an issue. But if you think about this whole thing, if instead we would have so fast immediate mode rendering path that we don't need to cache these things, we can change everything dynamically. In that case, we don't need to bind these things. We don't need to ahead of time compile these things. We don't need to do these hash maps that combine everything. But of course, that's, like, people say, that's the same thing that we had in DirectX 11. It was slow and bad. But the thing is that the modern hardware is different. And modern hardware is able to do bindless resources, for example. That's for the binding parts. So now you don't need to say that I'm binding these 5 textures and you need to know them, and you need to cache this particular set of 5 textures that is on this material. You need to store them in somewhere in GPU memory, in Vulkan or DirectX 11 descriptor heap. You are storing it. You need to pre-create it. You need to pre-create all of the permutations. But nowadays, you can just put one big descriptor heap. You put all of your textures that are in memory. They are in one big array on GPU memory. Like, not the texture itself, but these kind of small descriptors that say, like, where the texture memory is, like what is the format and dimensions and whatever. And the GPUs are using those. And now instead, like, the shader can say that, okay, I want to take a texture at slot 5, this is my texture. I need to take a buffer at slot 10, this is my buffer. I'm sampling the buffer at slot 10, I'm sampling the texture at slot 5, and the shader can do the decisions. You don't need to bind anything. You just somehow provide the shaded data that, okay, texture is on slot 5 and your buffer is on slot 10. So you don't need to do that. The hardware will not actually do anything. The hardware allows you to dynamically index to different textures. The hardware has all the functionalities. Even on NVIDIA, you can, every lane on a SIMD can sample different texture. They have done this optimization to make ray tracing even faster. So every lane could have a different texture index, and it still would do it a single instruction. And of course, texture sampler would internally run multiple times and combine stuff. So it is super efficient. There is like hardware support. NVIDIA, AMD, Intel, they have had it for multiple generations. Every mobile vendor has support for this bindless. They have different kind of quality, like some support per lane things, some don't. Some have slightly bit worse code quality, but regardless, like everything, like at least 2 or 3 generations on mobile and on PC, like 4 or 5 generations have supported now this. So it's everywhere. You can do it. You don't need to do any of these binding groupings anymore. So that's important. It was introduced back in the day on DirectX 12 shader model 6.6 on the first time, and then Vulkan recently added an extension that is basically supported now by everybody, except for some mobile vendors, of course, and except for all of those old Chinese mobile phones that never get driver updates anymore because they only get 2 years of driver updates. So of course on mobile you cannot do that yet because you have to support old phones that kids are using because their parents gave their 4 years old phone. But on desktop or console, if you are doing, you can just do it. One other thing that was introduced was that GPUs gained support for 64-bit integers. They got 64-bit integer pipelines and 64-bit pointers, and they now have full 64-bit virtual memory system like CPUs. So everything is virtual size, 64-bit pointers. Your descriptors, like in the descriptor heap that I was talking about, the texture descriptors also have 64-bit pointers inside them pointing to the texture data. So it's kind of like indirection in a way, but the sampler is caching those descriptors immediately. But if you don't want this indirection, you can directly use that 64-bit pointer in the shader. So the pointer can directly, like C code, C++ code, it can directly read any memory location with a 64-bit pointer in GPU memory.
How does this happen? Like, this is the one thing that I don't like. This was not possible like 10 years ago, right?
No, it's been possible. AMD GCN actually had it already. Like if you have like this Xbox One and PlayStation 4, they already had it kind of. That you could do it. The shader language, like that's the different thing. HLSL doesn't have support for 64-bit pointers. You cannot write code like that on your shader. But AMD had this flat addressing mode for 64-bit pointers. I think it was actually GCN 3 or 4, so it could have been like PlayStation 4 Pro or something like that, the first console, but I don't know if Sony actually exposed it because the shader languages back then didn't support it. It was mostly for like OpenCL code or like CUDA, of course, on NVIDIA, like heavily using that. So, but OpenCL was not really successful. Now it's rocking for AMD, and then of course on Metal you have like Metal is C++ based shader language like CUDA. It has similar. It has full support for 64-bit pointers and C data structure and so on. So in Metal you can, like if you have persistently mapped GPU memory, you can just write your CPU like structure there, like same with CUDA, and then you can just give a pointer to the shader that, and the shader can directly read your C structs just like that. Same in CUDA, it just works like that. But on Vulkan, it nowadays works. There is a buffer device address extension, which is actually supported by every mobile vendor as well, like on desktop as well. But it doesn't, like the GLSL shading language doesn't have pointer support. So it is really hacky to use. You need to use 64-bit integers and then kind of cast them to pointers with this really awkward syntax, and then you can access the memory. So it's like really, and you need to either manually do array stride accessing by manually calculating the address, or use this other horrible abstraction. so the language, because the language is like HLSL and GLSL were written for this really simple pixel and vertex shaders, like one element is one lane and so on. They were not written for compute shaders or SIMD processing or any of that. They were not designed for that. So that's kind of the big issue, that these two most popular shading languages are not really good at running pointer code or this kind of modern code with compute code. But Metal and CUDA and OpenCL also has a C++ based shading language. They are kind of supporting the modern GPU feature set. And of course the AMD's new compute API that is similar to CUDA. And this is where the research is nowadays. Like everybody is improving their compute capabilities. Like of course, like AI is everywhere, and AMD has loading instructions. You can directly load from memory to your group shared memory in a way that it doesn't need to even go through the registers. There are a lot of these kind of improvements on the hardware that if you use these raw memory load paths, you can get things faster. They don't need to go through the texture sampler. Like old GPUs, like all the memory loads were going through the texture sampler. But now these raw memory load paths, they go directly from your L1 cache to your registers, so the latency is much lower. So you can, on these modern workloads like Nanite, for example, that every pixel is loading like the triangle ID, and then from the triangle ID it's unpacking the triangle ID and loading instance IDs, and then from the instance ID it's loading your mesh matrix, and it's loading the whole like matrix on every pixel, and it's kind of loading every triangle vertex corner and transforming them inside the pixel shader and all of their attributes. It's doing a lot of these direct memory loads, and they're quite coherent because usually triangles are more than 1 pixel. Of course, in Nanite they can be 1 pixel, but usually they are sharing some data between neighbors. So the L1 cache latency is super important. So you try to kind of make the code, like even though they are raw memory loads and you could index to anywhere, you still want to make them cache coherent. So you are doing a lot of repeated loading from the L1 cache. So nowadays, modern GPUs have really fast L1 caches, and you want to be directly reading the L1 cache instead of going through the sampler, which is like, sampler can be like, how many? It's like, could be like over 3 times slower to go through the sampler on the latency side compared to like directly to the L1 cache. Of course, if you have a lot of occupants, a lot of extra threads, you can hide the latency, but then like you have other issues. Like usually you don't get that much because modern shaders use a lot of registers, they are complex, and you don't just want to add extra latency. So if you can use direct raw paths of memory, then you should use them. So that is kind of the thing. Now you can use 64-bit pointers. Now you can directly index your data index your textures from one big heap. So basically on a draw call nowadays, you can just put the one pointer to the shader and say that, okay, your root data is here. Like the shader can read the draw argument and the indices to texture that whatever it wants from that pointer and render anything. So you don't need to. It's kind of similar than if you have a C or C++ or Windows, like whatever operating system thread launch API, you are launching a thread, you give a context pointer, and that's it. Like the operating system doesn't have to know that, okay, I want to give these and these and these pieces of data and in this layout or whatever. You just give a pointer, the data is on memory, just go and get it. And that's exactly how the graphics API should work. The graphics API should not know anything about your data layout. It should not care. It should kind of like, you pass through a pointer and from your C code or C++ code, and the shader can directly read it. Like it's your responsibility of like putting the data in a good layout, and the shader can read the same thing, and the graphics API should not be bothered about your data at all. It should not know about the data. It should just pass through the pointer, and your shader can calculate, of course, offsets to that pointer or whatever it needs to do, like to kind of access different data. And that's kind of the design in a way that you don't need anything more than that. And this makes a lot of things more simpler, because then when you are doing a pipeline, you don't have to describe all of your bindings, like whatever data you need to do, and so on. And this solves one of the issues, like this solves the binding issue that you don't need to do these pre-combined bindings. But of course, like you need different solutions for all of the blend states and so on. And the blend state issue and all of these different like render states, which are still fixed function hardware in many GPUs. Like the bindless is nice because the texture samplers on the GPUs have improved so much that they are dynamic, because you need dynamic texture addressing for modern workloads like Nanite or ray tracing. So everybody has good dynamic paths nowadays. But for rasterization, it's still like quite hardware specific, and different hardware want different states on the rasterizer when they set up the rasterizer to do something, to do the C buffering or do the blending or whatever. And for this, you need to really think about, like, look at the hardware, what kind of hardware we have, like how they set up everything. And all of the hardwares, they have some kind of packages. The hardware driver will do some kind of like data packages, like low level basically commands, which it pushes to the command queue. And none of them have like one package to do like pipeline state object. They have small packages. They have rasterizer package, they have blending package, they have whatever packages. And this is the thing, like we should, because if the hardware is operating on these smaller packages, it's not operating on the DirectX 11 style that we can, or OpenGL, that we can set every different, even small piece of data separately, but it can set all of the rasterizer states separately. It can set all the blending states separately. And in Metal, for example, there is a separate package for configuring the depth density state. Like it's not in the pixel state of like PSO. It's a separate package. You can separately set it or not set it. And this is completely doable on like other hardware as well. Of course, there are some technicalities like on HypeHype and so on. Like I don't want to go on all of these technicalities because there exists reasons why people don't want to talk about these issues. But these are solvable issues. Sometimes maybe you need to keep like 2 copies of some state or something like that. It's not like if you have like, if your state is incompatible with HypeHype, for example, and you need to do a slightly bit different shader, then sometimes, yes, in certain cases, you need some kind of driver handling on something, but this is much less complexity compared to the whole thing that we have right now. You need a couple of these small things on certain hardware maybe, but in general, like putting everything together was a bad idea. And now we should have like in the middle ground, like we tried this, it was bad, we tried that and it was bad, but here is the right place. Because when people configure like C buffer, for example, they don't need to, like, usually you configure it once per draw call, or maybe then you have like some Z pre-pass, and then after the pre-pass you configure it again. So it's a couple of times per render pass. You don't need to configure it for every pipeline state object. And then on blending, most shaders don't even use blending. Like, who cares? Like, there are some shaders that use blending and then you change the blend state or the blending state and so on. So this is, for me, this feels much better that you actually get halfway there and actually investigate like how the modern hardware works. You don't need to think about like anything about 10 years old hardware, just a couple of latest generations. Like when DirectX 12 and Vulkan were launching, they were only talking about a couple of latest generations and dropping everything else. And now we could do the same. We drop everything else. We just take a couple of latest generations and everything else dies. Of course, it again would take like 5 years or so to get the adaptation to be high, but we could do it. And we could also, on mobile, we could take the latest 2 or 3 generations on every mobile vendor to be supported. So in the same way, like the Vulkan was supporting a couple of latest generations, we could do that as well. So it's kind of like time to start talking about, like, now it's like over 10 years from the launch of those APIs. Maybe we need the DirectX 13 or Vulkan 2 or whatever. We want this new thing to be called, like, throw away the old, like, really complex binding APIs, throw away, like, the bad idea that everything needs to be combined together, and make this new API and kind of throw away all of the old complexity, because now you can just, GPUs can access memory, and yes, like I said before in HypeHype, CPU can write directly to GPU memory nowadays. You have PCI Express rebar, or you have unified memory access on mobile devices, on integrated GPUs. So you have either one of those. So you can write CPU, can directly write descriptors to GPU descriptor heap. You don't need to do any memory copies or any complex APIs, descriptor management APIs or whatever. You just write them there. Like the Vulkan's new descriptor buffer extensions allows you to direct, like if you have one of these platforms, which is basically everything now, you can just directly map the whole descriptor heap to CPU visible memory, and you can just put the descriptors there. And it's on GPU memory, but CPU can see it, so it's really fast to access the GPU. There is no PCI Express like traffic going for every draw call, and it is basically the same thing as DirectX 12 heap management APIs do, but it actually doesn't need any APIs. Like that's the thing. Like you can just memcopy there. You can just like write there. It's super nice. Like it's just like a linear block of memory, and that makes it so much nicer because you don't need to somehow describe your data layout, kind of do your own reflection. Like all the graphics APIs, all like you need to write your own reflection code and reflect everything and kind of map everything together because you have to tell it to the graphics API, and this is my layout and so on. But you don't have to do it. You can just share your header, like write one C struct in a header and include that to both your shader and your C code, and that works. Like both can read the same struct just fine. You can just pass the pointer between them and everything is virtual memory, so the pointers work. Of course, you have a different memory space. Like you cannot directly, if you have CPU mapped pointer and GPU pointer, they are different. Like in a way, like they are slightly bit different pointers, but you can still do pointer math, you can add numbers to a pointer, you can index pointer and so on, like even GPU pointers, even though if you cannot access them directly. But some GPU pointers that are visible to CPU you can access, of course.
So technically speaking, if like this were to happen, who would need to take action? Would it be Kronos Group for Vulkan, designing the Vulkan 2.0 and other like authors of graphics APIs, or would this need to be like GPU vendor producers doing some like final touches to the GPU architecture? Like what would be the next step if we already envision this nice future with this like super simplified API? What would need to happen now?
I wrote about like the compatibility and compatibility layers also in the blog post, like how you kind of make modern code run on the new API or the current code run on the new API. So many of these APIs are really close to the new thing. Like if you take the newest Metal version, it's really close. You just need a couple of things and then you could basically run that kind of code. There are some things that should slightly improve to make the quality better, and also like some like that would allow you to run this kind of code, but it would still not be perfectly clean because Metal bindings APIs, for example, they work also on Metal 1 because they are backwards compatible, and by default they are automatically tracked in a way that you don't have any barriers. So you cannot push like GPU pointers directly through that same kind of API because that DirectX 11 style old API still needs to have kind of like this managed handle that it needs to kind of the driver internal needs to do something. So yes, it would be nice to have like new API that is not backwards compatible so that you cannot kind of compile your old Metal code on it. But on Metal side, because the shaders are directly like CUDA, like they are similar C programs that have pointers and you can do everything like that. It means that the shader ecosystem could be completely unchanged. It could be the same, assuming that Metal gets the descriptor heap thing. And this is something that I actually was talking with some Apple guys that. If we just had this one thing, then that would actually work. They had a new thing on Metal 4 that allows you to allocate from their internal driver descriptor heap like a big block of descriptors, which are contiguous, and you can bump them like they are like you can do pointer arithmetic to those and to find the next descriptors, and you can do that on CPU side, but they don't have any shader instructions to actually index them. You can hack it on a shader. You just reinterpret cast it to a pointer and then do arithmetic and reinterpret cast it back to texture handle and it works. It just works. But of course it works because the memory layout is like that. You know that it's like that because that's on your CPU side. You know that because you get the memory on CPU and you can just write it there. So yes, it's guaranteed to be that memory layout, and you know it, but they just don't have like the syntactic sugar to kind of index those descriptors on the GPU side, like the texture handles. So it would be nice to have that, and if you would have that, then Molten VK also would automatically be able to support the new Vulkan descriptor buffer extension, which is basically the same as DirectX 12 ShaderMole 6.6. So basically, then Metal would have everything. So it's kind of doable if you want to hack it already, so you can have everything on Metal. But of course, hacking is not as nice as really clean and nice API because the whole point of my talk is that we wanted to make clean and the fast default path so that all the tools working and everything is working, and this is the way everybody writes code, and nobody has all of these old legacy ways of doing things are stripped out because they are just more complicated and just make everything more complex, harder to understand. And this, like on Vulkan, yes, you have everything already. You have the buffer device address, but like I said, like GLSL doesn't have pointers, so you have to hack it with reinterpret casting basically 64-bit integers and passing them around like typeless integers and whatever. It's messy. And then the descriptor buffer is exactly like I described in my API. It's like fully like CPU writable and everything. So that's there. They have pretty much all of the stuff, but so much old API bloat. Like most of them all. Like it's massive API. If they would strip it down for Vulkan 3 to just get it and have a new shader language. But they need a whole new shader language, which is a big deal. So, or like have proper pointer access on GLSL. But one extra issue with GLSL and HLSL is that because they don't have pointer semantics, like it's so difficult to work with functions. Like you cannot pass like for example, if you have a uniform buffer and you have an array inside the uniform buffer, like you have some structure and some array inside the structure, you cannot pass that array to a function. Like there is no way. The languages, like HLS and GLS, they don't support that. There is no way. And same thing, like if you have a group shared memory array, you cannot pass that to a function because there is no pointers. There's no way to represent this kind of like slice of memory. Like they simply don't support that. So that's really awkward because then when you are writing like one reason why CUDA and NVIDIA is a $5 trillion company nowadays is that CUDA is really nice for writing reusable code. It has all of the same functionality that C and C++ have. You have really nice function. You can write code using function. You can write libraries. But ELSL and HLSL, they don't have libraries. And one of the reasons for that is that you cannot even pass arrays to functions properly. So like how you make a like ecosystem of libraries if you cannot pass like pointers or if you cannot even pass arrays to functions properly. So you can pass fixed size array, but the code chain is sometimes really horrible. Like you should not do that. So that is kind of the reason that these languages, they already have problems, even if you don't like pass 64-bit pointers directly, because they cannot really have this kind of proper like pointer semantics to addressing to a sub array inside a resource or whatever. So that makes writing libraries bad on those languages. So yes, I would really love that GLSL language and HLSL language would be either revamped. They have some really nice qualities, like the vectors are, for example, nice, all the vectors, visuals and so on. Like people like writing math code with that. But the whole thing that there is no proper support for arrays and pointers is kind of dragging down, and it's kind of making it so that you cannot really build a library ecosystem like CUDA has. And because CUDA has a library ecosystem, that's why NVIDIA is the most expensive company in the world, because it's not about the GPU. Of course, they have good GPUs as well, but the CUDA ecosystem is super important for them. Like it kind of gives them the vendor lock-in. And it's a good language. Like it's simple, and you just have one kernel type. You don't have this massive bloated like graphics. Like let's not talk about that topic, because I will write a blog post about like the whole like shader, like how many different shader entry points we have, and for every single purpose, like somebody thought that it would be nice to tessellate on GPU, and somebody let's do this geometry shaders and whatever, and all of these failed, except for like all of these were really slow, and they failed because developers just wrote computers instead. But now ray tracing is also really slow, but the hardware vendors have been optimizing it all the time. It has some use at least, but it's if you put enough hardware on it and enough like really specified hardware box, then yes, it can be made fast enough. But it's like I would say that right now it's the inflection point. If you have a really high-end GPU with all of the most modern hardware technologies that can do per lane IPs and can do per lane heap indices and can do like all of these like shader order reorderings, like that you can take your register from multiple waves and then you can swizzle them together to get the branch coherence to be better, like NVIDIA can do, and Intel also has the same thing. Then yes, it's starting to become usable on high end. If you write good code and if you understand the data access patterns, but ray tracing is like hash maps. It is kind of similar issue that most of the ray tracing algorithms are randomizing the rays because you are random sampling some kind of cone or whatever. So you are purposefully trying to randomize it so that it has the biggest spread available so that you can accumulate the samples. So it has kind of the same, like it's doing the same thing that the hash maps. Like ray tracing is just like hash map on 3D, basically. 3D space hash map in a way. So not like if you do primary rays or shadow rays or whatever, but if you do these kind of, you randomize your rays, which is common on many algorithms like path tracing, for example, that you are randomizing your rays and trying to kind of find the best paths and so on. So it's kind of inherently bad for memory access patterns. So you need massive caches, and you would need to be sorting the rays and doing whatever optimizations you can do to improve the locality. But then again, if you want this easy API that you can just throw a race around and every lane can just throw a ray around, then the problem is that in that case, you are not solving the hard problems. You are not sorting your rays and you are not binning the rays and whatever. But if you do it manually, then you can get a really high performance improvement. But then the reason is like, why would you even have this API in the first place? You could just have an intrinsic to kind of use the hardware intersectors to get the collision point, and then because you are binning it anyway to some other computer or whatever, which is running it later, you don't really need the ability to run a payload, like separate payload per lane, for example. You don't need all of these machineries. So it's kind of like what some people have been doing, that they do it manually and they are binning it manually and they are getting big performance gains. So, but nowadays, of course, because the hardware has improved so much, you still get benefit from that, of course. But if you have bigger caches and all of these different things and different like things that kind of allow you to combine things in a waves in a way that reduces the problems, then you can kind of get away with that. But it's still like, it's better than like when I saw the first Battlefield 4, what was it, Battlefield 4, and there was some kind of ray tracing path on it for reflections, and NVIDIA was showcasing their new profile at SIGGRAPH, and you could see clearly on like their slides, and you can zoom in, and GPU utilization 8%. Like it was like the ray tracing path was like 92% of the GPU was idling during the whole ray tracing path. It was like SIMD utilization 8%. So that's like, yes, okay, this is efficient. Like, but of course it's improved since, but that's like, if you think about like why ray tracing is slow, it's not slow because it's utilizing the SIMDs. It's slow because it's not doing anything. So that's kind of the reason. The reason is that the workload is so bad that the GPU is just waiting. If ray tracing would be utilizing the whole GPU, then I wouldn't be even saying anything critical, because then everything would be good. But if it's like you are waiting for memory, or you are like waiting for scheduler or whatever, then of course, like, it's not really the best way to spend the GPU. In that case, if you have such a low utilization, you want to offload the heavy processing to separate steps, and then kind of write your ray results to memory and bin them properly, and then run in computers which have 100% utilization. So that's the thing. Like, if your path has poor utilization, then just run it elsewhere. But if you do that, then why would you have this kind of complicated API that kind of makes it you believe that you can run a virtual function call per lane, which is basically like every lane can collide to different material which invoke different shader. It makes you believe that every SIMD lane can run a different shader, but of course it cannot run it, and some magic has to happen to kind of make you believe that it's happening. But maybe you don't need it. Like, if you write code like that, then you don't need it. And there has been like many industry veterans saying that maybe we should run it like that. But of course it requires more, like, it requires more senior programmers to write code, because people just like that, okay, I can run these virtual functions on my GPU, like every lane is hitting different thing and it just works, and somebody just solves my random memory access patterns, like using hash maps everywhere. It's kind of the similar problem. But it's like, personally, when I'm seeing those, when I'm seeing the numbers in my profiler and the GPU utilization is so low, like 8%, I'm seeing like, maybe the design should be different. Maybe there should be a little bit more effort on the developer side, because nowadays everybody is using Unreal Engine or Unity or like God or whatever. Or like EA is using they have a one engine, like they have Frostbite nowadays in every game. Like, you don't need to write it many times. And if you have a good language like CUDA, for example, CUDA has libraries. Somebody can write a library for that it does good fast ray tracing for you, and then you can use the library. But HLSL and GLSL are not good languages for libraries, like I said before. So it's kind of a problem in the serial world. But on NVIDIA as well, like, when you have a good language and good ecosystem, then people write you libraries. There's a massive amount of CUDA libraries, and people just use it, and they just improve the whole ecosystem that way. So yeah, I would say that this is kind of the problem. We like, if HLSL and GLSL are locking in, like DirectX 12 cannot improve and Vulkan cannot improve because the shared languages are the bottleneck, then maybe we should fix the shared languages as well. And then you can get the modern bindless things and pointers and everything on it, and then it just works. And that's my opinion, of course. Like,
that was a short summary of your blog post.
Yeah, I think we have been talking for 3 hours already.
Yeah.
But yeah, this is the reason I'm so vocal about this, is that I have been using these graphics APIs for so many years, and I have seen their issues, and I have been trying to write graphics code, kind of sidestepping the issues on many big companies for many big graphics APIs, and kind of trying to abstract the APIs and do whatever to get most of the APIs. And it is kind of painful in a way. And this is one of the, like, I just wanted to get it out of my system. Like, like this was supposed to be a short blog post, but it's like 50 pages or something. And my wife, like, who is a PhD, she has said, okay, this is not a blog post. This is like a book or like whatever, like or like a big academic paper or something, or dissertation. But I'm just like, yeah, this is a blog post, like 50 pages. It's like I just had to write it because these things should be fixed. Like somebody should kind of talk about, like, so that also the hardware vendors understand, like, what is the situation on developers, like what is the pain points that developers are having. And this is kind of my way to saying that I have been talking with so many graphic engineers in so many companies, and nobody really likes these APIs, or at least the Vulkan 1 and DirectX 12.1. But now that we had shader model 6.6 and so on, and we had binder resources and everything, it's again that graphics programming is fun again. Like if you have these APIs, if you exactly are targeting some platform and only writing to one API because these are slightly bit different, it's kind of hard to remap them together. Actually, Valve has been doing really good job on Linux side that they made the buffer, the Vulkan's buffer tech, perhaps it's called like descriptor buffer extension, which is kind of the shader model 6.6 heap, because they have to port all the Windows games to Linux on the Steam Deck. So they have to kind of like, people have been writing this kind of code, and people who write ray tracing, they really like binder resources, because ray tracing without binders is really horrible, because then you have like every ray can hit different texture bindings and different bindings as well. So it's super horrible, because then you put on the big pipeline, you put this so many different binding groups and everything on it. It's horrible. So everybody who are doing ray tracing, they are just using the big binder heap, and because otherwise it would be really horrible. And on Vulkan ray tracing, like if you use the Vulkan ray tracing without this thing, like yes, you are using descriptor sets everywhere, and it's not nice. So it's nowadays like if you have the right API and if you only support the latest GPUs, and if you write a hobby project, you can have fun with the GPUs again, because now you write bindless, you don't care, you don't have to update your CPU binding codes or whatever. You just put bindings there, and then you can just write shaders and make shaders do whatever you want, and don't even touch the CPU side anymore. And some people are just prototyping like that. They have some really small stub that is starting your GPU running some compute shaders, and they just write everything on there. So it's nice. That's super nice, and I would hope that graphics programming would be nice again. Like people had fun with DirectX 11 and OpenGL back then, but nowadays, like it's like, yeah, I'm writing. Before I can write this feature, I need to write the driver myself, and then it's complex. Like it's super complex. So yeah, that's. I kind of like, I'm expert on this, so I can do this, but I don't like writing like all of these barrier synchronizations code. Like it's, yeah, of course I have job security. Like I can, I even rewrote some of the Unreal Engine Force barriers back in the day for Xbox, or not for Xbox, actually for PlayStation, but it's, I don't like the job security. I just like it to be
You would
solved.
like to
Like
lose
nobody
it.
should be doing this thing, like, because it's like, it's a thing that there is better ways to solve it. Like the barrier, like I had the simpler barrier API proposal, which is kind of based on the thing that GPUs don't care about resources. You don't transition resources to a different state. People think that it works like that because they have all seen this abstracted API, so they don't even know how GPUs work anymore. GPUs only, they are mostly coherent nowadays. Like most GPUs, actually all the new GPUs have coherent last level caches. So you don't need to never flush the whole cache hierarchy to memory, which is really big improvement. But some low-level, small, tiny caches like rasterizer caches or L0 caches or whatever, they might be uncoherent, and sometimes you need to flush them. And this doesn't require any list of resources. There is no like range flushes or whatever. Like I'm flushing these certain bits from this memory location. Like no, none of that exists. There was actually some GPUs that had it back in the day, but not anymore. Or at least drivers are not using that. Maybe somebody still has those old code paths. But the thing is that when you want to flush those caches, you can just say that, okay, I want this barrier, but this barrier gives more visibility on this. So you just say some bit flag that, okay, this time I want rasterizer caches to be visible here. And then the GPU does some flushes the internal small caches to the last level cache, which doesn't actually create any memory traffic because it's like small caches to big caches. Or it can even mark those lines as dirty or whatever if they are just read-only lines. So all of this is like really simple nowadays, but still like the old API, the old way, the old tooling especially, is that all of my resources are in some state, and I need to track the states. And when I'm recording it from multiple threads, I need to know that okay, some other thread is record like if you have multiple command buffers, you are going to submit them in certain order, and you need to know that okay, this previous command buffer put these resources in this state, so that you have to say always to the API that the last state was this, and you are parallel recording them. So there are a lot of hacks on this. For example, Unreal Engine is doing these tiny command buffers between these two command buffers to patch the resource states, so that you can just say the state has changed, but the GPUs don't care. It's just no op. Like the driver just ignores all that stuff, and they are submitting a new command buffer that is basically empty and does nothing, just because like the API requires that for the contract. So it's not good. So it should be fixed as well. The barrier should be fixed. So that's something that I'm really feel heavily about. And there are some other aspects as well. Like I will be talking about the share ecosystem, like how it should be fixed. But that is a much bigger talk, and that also might require some hardware changes. None of that what I am talking in my blog post would require any hardware changes. Of course, like some GPUs might need to work a little bit on certain things. For example, it would be nice on AMD, like if you are accessing like 64-bit pointer, your index also needs to be like, you have a pointer and index, like normally like your array addressing. It would be nice that if you have a 64-bit pointer and 32-bit index instead, because 32-bit indices take like half amount of registers. Like that's the normal thing that you do with buffer, you have 32-bit index, but you could have a 64-bit pointer and 32-bit index, because it's just like your load instruction could be so that you have one shared 64-bit index and then you had per lane 32-bit index. And that's the same way that some hardware architectures are actually doing that, or they are doing that for the heap addresses, for example. There's one shared 64-bit address, and then there is like one per lane 32-bit address. So like all of these improvements, like people have done the same thing for texture samples, for example, that they support 16-bit UVs. So the UVs are smaller. So all of this is like to improve the register utilization. So, and there are some missing instructions somewhere for some conversion instructions on some hardware. For example, unpacking works in, like you can pack, but you cannot unpack, or you cannot unpack certain formats or whatever. It's just missing for some odd reason. Like the other instruction exists, but there is one instruction missing or something like that, and then the GPU has to do, the compiler has to kind of work more on that. But all of these things are like, yeah, let's add one instruction there because we already have like hundreds of instructions, like who cares? So it's completely solvable. Like if you would have this kind of ecosystem, like, and if the only problem is that, yeah, some GPU runs some shaders slightly bit slower and needs one or two instructions more, it's not the problem, because most shaders are not even ALU bound nowadays. Like they just doubled AMD, NVIDIA, they doubled their ALUs. Like, and that gave them like 30% performance boost for double ALUs. Like they have double pipes nowadays, like both of them like doubled their pipes, and they only got like 20-30% gain. So it clearly shows that the shaders are not ALU bound. Like if you put more ALU units, like with the current shaders, like it's not going to be, the ALU instructions are not going to be a bottleneck. Like memory is starting to be a bottleneck, or other things. Of course, at some point, yes, people will put even more instructions in their shaders, and at some point they will be bottlenecked again. But at least currently, like most shaders are not ALU bound.
All right. Can you tell me, where can people follow your work? Because we mentioned Twitter, but we mentioned the blog post, but we should spell out like how people can find you and to be up to date with what you do at HypeHype or generally.
I'm active at Twitter. Like, so Seb Aaltonen is my Twitter handle. So I'm posting there almost daily. Like we are using a lot of AI today, and I'm just putting my agents to run, and I'm tweeting. But of course, I'm writing code as well now, like engine code. Like for me, it's super important to kind of realize that some prototyping code has lower quality requirements, you can use AI to write it. You can write it more sloppy way. But then when you write engine code as really high performance code, it's like something that you need to handwrite today. So yeah, but I have more time nowadays because I have sometimes I'm just waiting for my agents to finish,
What do you
and we are
use?
prototyping a lot now because we are doing AI stuff, and we are learning how to use AI and so on.
What do you use as far as AI tools are concerned for the code?
A lot of different tools, but for me, like I'm mostly using Codex for writing code, and yeah, we like if I'm integrating LLMs because we have our own AI platform, it's like I'm going through a lot of different models and seeing like what they do, like for our scene creation tools and so on, like that I'm iterating right now on. So yeah, it's on kind of like for our tools, it's mostly for me it's important. Like of course quality is always important. AI is still like not doing good enough quality, so you always want the biggest, best models. But when you are doing rapid iteration, you need kind of you use LLM with some tool and you give tool interfaces, and the LLM is conversing with your tool. It's kind of doing round trips and calling functions and whatever. Then you really need performance as well because the LLM might be like doing 20 different round trips and discussing. It's not discussing with you, it's discussing with the computer. It's discussing with your scene management tools and whatever. Like it's doing like queries to your ECS system or whatever, like to understand what's happening on the scene and then modifying it and so on. So then in those cases, yeah, performance matters because there is iteration and round trips and so on. And of course, like, because I'm an optimizing guy and I'm doing tooling, like I'm always like debug outputting everything and what kind of tokens is going on everywhere, and I'm optimizing the round trips and tokens and like how the model works and everything. I'm just like everything is an optimization problem for me. So when I'm writing LLM tooling, it's all about like how we can minimize the token counts and minimize the time and minimize like the round trips and everything. Like, but when I'm talking to an LLM, like then it's a different thing because I'm yeah, it's different thing compared to like when I'm writing tooling because I'm writing it to somebody else and it needs to be good. So for me, it's like I just one shot some like not one shot, but I'm doing something and prototyping, and the prototyping doesn't have to be how would I say it? Like prototype code is different compared to engine code, and prototype code has like it's like you are trying something and then you are throwing it away. So it's really nice to do throwaway code with AI. But then when I'm doing tooling, I'm kind of expecting the tool to be used a lot, and then the tool is using the LLM a lot because it's doing a lot of iteration. Like that iteration loop needs to be super efficient. So it's kind of a different thing when I'm using LLM myself or when I'm writing LLM to computer interfaces because it's it's a different thing, and it's actually a nice problem to optimize as well. Like if you have seen like the news and like these big companies, they are like, yeah, no, our LLM tooling is like 10 times faster or whatever, and somebody just like fixed the like it's like these guys have been just like doing like brute force thing, like spending more and more and more and using these nuclear power plants to train their things, and now you have seen like first times you are seeing that suddenly like there are models that are much faster and they still are doing a good job, and they are smaller and they are like 10 times cheaper per token, and like it has to happen. Like now people are optimizing their AI stuff, and of course when I'm doing tooling with this algorithm, I'm really like this kind of person who wants to understand what's happening, and even if it's not a money issue, less tokens means that it's running faster and then it iterates better. And game development is all about iteration. And if you have less tokens, it means that you have more important tokens that actually matter for the problem. Otherwise, you have more noise. And of course, like if you put more noise to any kind of like the person or AI, it will do a worse job. So you kind of try to improve the focus so that it actually gets the right data and fast, so that it doesn't have to do more round trips than possible. So that's kind of like the thing that I'm doing with AI, and that actually is fun for me. Like I'm not like uh, it's kind of like an optimizing a system. And then when you see it's actually doing something, and then you see the quality improving, and then you see that it's actually running like 10 times faster than the last time, because you just change it and you change the APIs and made the LLM to understand your stuff better, then it can do a better job with the APIs. And it's really interesting to see like how, if you are spending the time, like I'm used to, like I have Profiler open, I'm just iterating and iterating and iterating, and I can do the same with AI systems, and I can get them like 10 times better in one day, and that's kind of really nice to see that if you actually put effort, like the AI could do much better job. But most of the AI tools, they are just like somebody just scripted it together and didn't even care about, and it could run much faster and create much better results. So I'm kind of optimistic about AI because of this. And then even the model creators, they like the guys who are training these massive LLMs, they are like putting more effort to actually make them more efficient. And now you have big models, like you can run a model that is as good as ChatGPT 4.0, which was still like the most used model last summer. Like everybody was using ChatGPT 4.0 last summer, and you can run a model like that locally on your GPU. And that's kind of the thing, that it used to require a supercomputer to run that kind of AI. And now you can just have it. I can just compile it locally and run it on my GPU, even on my laptop. And it's kind of interesting, like how far these models have gone. But of course, ChatGPT 4.0 is not like the best model. Like it's not. Of course, you want better models, and I want better models, and I'm using the best models. But if you think about developing countries and people like AI in scale, having cheap models that you can run like locally, you can deploy at some point on a phone. So they can run on any phone. You don't need to pay anybody any fees. There is no monthly cost. There is no data. There is no, you don't even need the internet connection to use that. That's kind of like the way that when everybody has that kind of AI, and ChatGPT 4.0 quality is like could be completely fine for somebody who's not doing any technical tasks. They are just asking like some, like maybe they didn't even have a lot of schools, or like couldn't attend or whatever, and they have this information, and it's kind of useful for them. So for me it seems that it's the local AIs are actually like now being relevant. Like OpenClaw, if you have used OpenClaw, it's kind of a big thing right now, as people are
Yeah.
using local AIs with that. People first time even know that local AIs exist, because like somebody packaged them in a good installer that you can just run it and you don't need to care about it, and then you have a local AI on your computer. Like most people don't clone a GitHub repo and pull a like some random AI model from Hugging Face or whatever. It's like people don't do it. Like people don't have that kind of experience. But if you package them really nicely on an installer and everything, and have good tooling, good user interface, and integrate it with your computer, I don't. OpenClaw is kind of like security issue, because it kind of gives access to your whole computer, and AI can do anything it wants. But this kind of shows that a local AI can actually do a lot of stuff, and now people are finally understanding it. And it can be a problem with some AI companies who are thinking that everybody will pay them like $20 a month or something soon, and now they think that we have like 5% of the whole world population, and soon we have like 20 times more customers. But maybe these people just run the cheap, like free open source model instead, that is like 5% worse than your model locally on their computer, or it's running on their school server or whatever, like their country server, or like because I guess that countries could also give them their like AI services if it's open source service. Like France has been moving away from Microsoft products lately because they don't trust that, and it might happen that these open source things get popular. Linux is of course really popular, like all the servers and everything. Like open source has that, but if AI becomes open source, like it's kind of like difficult to get back all the money, all the nuclear reactors that we use for multiple years to train the model. Like if everybody is using open source model for free, but let's see what happens. Like personally, I have been investing in hardware companies and hardware. Like people will buy the hardware. It doesn't matter if it's running on server or locally on your computer. You just need the hardware to run it. So it's fine. But if you are the software company that is just training a model and competing against all of these open source models, then it could be difficult. Like none of them are making money right now. So let's see how it goes. But there might be a bubble on the software side. But of course, NVIDIA will survive and they will buy some of the software companies that like the remnants and the networks, and they will be happy about that. But yeah, it's interesting to see what happens, but I don't trust that there is going to be a big like AI bubble that everything is collapsing. Like, of course, some software companies will collapse because they have bad business models. They don't know, like the way that they are making money, they are assuming that soon everybody is buying their services, but it might be that the open source ecosystem is still like more preferable, and then like what happens? But NVIDIA or TSMC or whatever the hardware manufacturers, they don't care like who is running the hardware. Like if people are doing inference, like they have sold the hardware anyway. So I don't think that like NVIDIA is going to be like gaming only manufacturer anymore, because now it's gaming is like 10% of the revenue. Like why would they be? Like that would be like collapsing the whole company, like if they try to do that anymore. So I think that AI is going to stay, but some AI software companies will be bankrupt at some point. At least some of them. Like maybe some will survive, but it's going to be interesting, like how they are going to make the money.
Nice. Sebastian, thank you so much. Yes.
Thank you.
Thank you so much for joining me for a 3.5 hour discussion.